Close your eyes and let yourself drift as we embark on a gentle journey through the cosmos, exploring the remarkable story of how humanity's most powerful eye in space has revolutionized our understanding of worlds beyond our solar system, revealing secrets written in starlight from planets we could only dream of just decades ago. For thousands of years, humans have gazed up at the night sky and wondered whether we are alone in the universe. This ancient question has driven our curiosity since the dawn of civilization, when our ancestors first noticed those wandering stars that moved differently from all the others. The Greeks called them planets, meaning wanderers, and these were the planets of our own solar system. But the question that haunted generation after generation of stargazers was whether there might be other planets, circling other stars, perhaps harboring life of their own. The journey to answering this question has been long and winding, filled with false starts, brilliant insights, and technological breakthroughs that seemed impossible just a generation before they happened. In the 1600s, the Italian philosopher Giordano Bruno was burned at the stake for suggesting, among other heresies, that the stars were distant suns with their own planets. His vision was centuries ahead of his time, but he had no way to prove it. The telescopes of his era, crude tubes with simple lenses, could barely resolve the moons of Jupiter that Galileo had just discovered. For nearly 400 years after Bruno's death, the existence of planets beyond our solar system remained purely theoretical. Astronomers could calculate that they should exist, based on our understanding of how stars form from vast clouds of gas and dust. When a cloud collapses under its own gravity to form a star, conservation of angular momentum means that not all the material can fall directly into the center. Some of it forms a spinning disk around the young star, and within this disk, planets can form. If this process created our solar system, logic suggested it should create planets around other stars too. But detecting these distant worlds seemed impossible. Planets don't generate their own light like stars do. They merely reflect the light of their parent star, and even the largest planets reflect only a tiny fraction of that light. Trying to see an exoplanet next to its star is like trying to spot a firefly hovering next to a searchlight from miles away. The star's overwhelming brightness completely drowns out the faint reflected light from any planets. Throughout the 20th century, there were numerous claimed detections of exoplanets that later proved to be false alarms. In 1963, Peter van de Kamp announced that he had discovered planets around Barnard's star, one of our nearest stellar neighbors. He had spent decades making precise measurements of the star's position, looking for the tiny wobble that would indicate the gravitational pull of an orbiting planet. His claimed detection made headlines around the world, but other astronomers couldn't confirm his observations. Eventually, it was discovered that the apparent wobble was caused by adjustments made to his telescope over the years, not by planets. The real breakthrough came in 1992, though not in the way anyone expected. Alexander Woolson and Dale Frail discovered planets orbiting a pulsar, the ultradense remnant of a star that had exploded as a supernova. These planets, orbiting a dead star that bathes them in deadly radiation, were nothing like Earth and certainly couldn't harbor life as we know it. But they proved that planets could exist beyond our solar system. The discovery that really opened the floodgates came in 1995, when Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b, the first confirmed planet orbiting a sun-like star. This planet was nothing like what astronomers expected. It was a gas giant like Jupiter, but it orbited its star in just 4 days, so close that its atmosphere was heated to over 1,000 degrees Celsius. Astronomers dubbed these unexpected worlds hot Jupiters, and their existence forced a complete rethinking of how planetary systems form and evolve. The method Mayor and Queloz used, called the radial velocity method, detects planets by measuring the tiny wobble they cause in their parent star's motion. As a planet orbits its star, its gravity pulls the star in a small circle. This causes the star's light to shift slightly toward the blue end of the spectrum when it's moving toward us and toward the red end when it's moving away. By measuring these Doppler shifts precisely, astronomers can infer the presence of a planet and determine its mass and orbital period. Following this discovery, the pace of exoplanet discoveries accelerated rapidly. Ground-based telescopes around the world began systematic surveys, looking for the telltale wobbles of planets. By the early 2000s, astronomers were finding new planets every month. But these early discoveries were biased toward finding large planets in close orbits, because these create the biggest wobbles and are easiest to detect. A new method emerged that would revolutionize exoplanet science, the transit method. When a planet passes in front of its star from our point of view, it blocks a tiny fraction of the star's light. By measuring this dimming precisely, astronomers can determine the planet's size and orbital period. The first transiting exoplanet, HD 209458b, was discovered in 1999. The transit method had a huge advantage over the radial velocity method. It could determine a planet's radius, and when combined with radial velocity measurements, astronomers could calculate the planet's density and make educated guesses about its composition. The transit method reached its full potential with space-based telescopes, which could make measurements free from the distorting effects of Earth's atmosphere. The French space telescope Corot, launched in 2006, discovered dozens of transiting planets. But the real game-changer was NASA's Kepler Space Telescope, launched in 2009. Kepler was designed with one primary mission, to determine how common Earth-like planets are in our galaxy. It stared continuously at a patch of sky containing about 150,000 stars, watching for the tiny dips in brightness that indicate transiting planets. Over its 9-year mission, Kepler discovered more than 2,500 confirmed planets and thousands more candidates. It revealed that planets are incredibly common, with most stars having at least one planet, and that small, rocky planets like Earth are more common than the gas giants that were easier to detect. Kepler's discoveries painted a picture of incredible planetary diversity. There were super-Earths, planets larger than Earth but smaller than Neptune, which don't exist in our solar system. There were lava worlds, so close to their stars that their surfaces are oceans of molten rock. There were planets orbiting binary stars, like the fictional Tatooine from Star Wars. There were rogue planets, wandering through interstellar space without a star. The universe, it seemed, was far more creative in making planets than we had ever imagined. But for all its success, Kepler had limitations. It could tell us a planet's size and orbit, but not much else. It couldn't analyze the planet's atmosphere or determine whether it might be habitable. Most of the planets Kepler discovered were too far away for detailed follow-up observations with existing telescopes. What astronomers needed was a telescope powerful enough to study these distant worlds in detail. To analyze their atmospheres and search for signs of habitability or even life. The Hubble Space Telescope, launched in 1990, had made some pioneering observations of exoplanet atmospheres. In 2001, it made the first detection of an atmosphere around an exoplanet, finding sodium in the atmosphere of HD 209458b. Over the years, Hubble detected water vapor, methane, and other molecules in the atmospheres of various exoplanets. But Hubble was designed primarily to observe visible and ultraviolet light, while many of the most interesting molecular signatures are in the infrared. Additionally, Hubble's mirror, at 2.4 meters in diameter, limited how much light it could collect from these faint, distant worlds. The Spitzer Space Telescope, an infrared telescope launched in 2003, made important contributions to exoplanet science. It created the first temperature maps of exoplanet atmospheres and detected various molecules that Hubble couldn't see. But Spitzer's mirror was even smaller than Hubble's, at just 85 centimeters, limiting its sensitivity. What the exoplanet community dreamed of was a large infrared telescope in space, one that could peer through the cosmic dust that obscures visible light, detect the heat signatures of planets, and analyze their atmospheric composition in unprecedented detail. This dream telescope would need to be much larger than Hubble, much more sensitive than Spitzer, and equipped with instruments specifically designed for exoplanet science. That dream telescope was already being planned. Originally conceived in the 1990s as the Next Generation Space Telescope, it would eventually become known as the James Webb Space Telescope. As the design evolved and the capabilities became clear, exoplanet scientists realized that this telescope would transform their field. It would be able to study planets that Kepler had discovered but couldn't characterize. It would be able to detect and analyze the atmospheres of potentially habitable worlds. It might even be able to detect biosignatures, the chemical signs of life. The path to building this telescope would be long and fraught with challenges. The initial cost estimate of $1 billion would balloon to nearly $10 billion. The launch date would slip from 2007 to 2021. There would be moments when it seemed like the project might be cancelled entirely. But the scientific community persevered, driven by the promise of what this telescope could reveal about worlds beyond our solar system. The James Webb Space Telescope represents one of the most ambitious engineering projects ever undertaken by humanity, a machine designed to push the boundaries of what we can observe in the universe. Every aspect of its design was carefully crafted to enable observations that were simply impossible with previous telescopes, and many of these capabilities are perfectly suited for studying exoplanets in ways we never could before. At the heart of Webb is its primary mirror, a golden honeycomb of 18 hexagonal segments that work together as a single surface. This mirror spans 6.5 meters across, giving it more than 6 times the light-collecting area of Hubble. This isn't just about size for the sake of size. When observing exoplanets, astronomers are often trying to detect incredibly faint signals, whether it's the slight dimming of a star as a planet passes in front of it or the weak infrared glow of a planet's atmosphere. Every photon counts, and Webb's large mirror can gather enough light to detect signals that would be completely invisible to smaller telescopes. The choice to make the mirror from 18 segments rather than a single piece was driven by a practical constraint: the mirror had to fit inside the rocket that would launch it into space. The Ariane 5 rocket's fairing is only about 5 meters wide, so a 6.5-meter mirror had to be folded up for launch. The segmented design allowed the mirror to fold like the petals of a flower, with the side segments folding back for launch and then unfolding once the telescope reached space. But creating a segmented mirror introduced enormous technical challenges. The 18 segments have to be aligned with nanometer precision to work as a single mirror. Each segment has 7 actuators that can adjust its position and orientation. After launch, engineers spent months carefully aligning the segments, using a special camera to measure their positions and making tiny adjustments until the segments worked in perfect harmony. The result is a mirror that performs even better than specifications required, delivering images sharper than the most optimistic predictions. The mirror itself is made of beryllium, a lightweight metal that holds its shape well at the extremely cold temperatures of space. Each segment was polished to an accuracy of less than 20 nanometers, smoother than anything you encounter in daily life. If Webb's mirror were scaled up to the size of the United States, the largest imperfection would be only about an inch tall. This incredible smoothness is essential for forming sharp images of distant objects. The golden coating on the mirror isn't just for show. The gold layer is only about 100 nanometers thick, thinner than a human hair, but it's incredibly effective at reflecting infrared light. Gold reflects about 98% of infrared light, compared to about 85% for aluminum, which is used on many other telescope mirrors. This high reflectivity is crucial for detecting the faint infrared signals from exoplanets. The decision to optimize Webb for infrared observations was one of the most important choices in its design, and it's particularly beneficial for exoplanet science. Infrared light has several advantages over visible light when studying planets. First, planets emit most of their own light in the infrared as thermal radiation. A planet like Earth, with a temperature around 290 Kelvin, emits most strongly at wavelengths around 10 micrometers, well into the infrared range. By observing in the infrared, Webb can detect the heat from planets directly, rather than just seeing reflected starlight. Second, infrared light can penetrate cosmic dust that blocks visible light. Many star-forming regions where young planets are found are shrouded in dust that makes them difficult or impossible to observe in visible light. Webb's infrared vision can peer through this dust to see newly formed planets in their birth environments. Third, many important molecules in planetary atmospheres have their strongest absorption features in the infrared. Water vapor, methane, carbon dioxide, and other molecules that might indicate habitability or even life absorb infrared light at specific wavelengths. By observing how a planet's infrared spectrum changes as it passes in front of or behind its star, Webb can identify these molecules and measure their abundances. To observe in the infrared, Webb has to be incredibly cold. Any warm object emits infrared radiation, so if the telescope were warm, it would be blinded by its own glow, like trying to observe stars during daytime. This is where Webb's iconic sun shield comes in. This 5-layer shield, each layer as thin as a human hair, is about the size of a tennis court. It blocks the heat from the sun, Earth, and Moon, allowing the telescope to cool to about 40 Kelvin, or minus 233 degrees Celsius. The sun shield is a marvel of engineering in its own right. The 5 layers are made of captain, a material that remains stable across a huge range of temperatures. Each layer is coated with aluminum to reflect heat, and the 2 layers closest to the sun have an additional coating of silicon to protect them from the sun's intense radiation. The layers are separated by vacuum, which is an excellent insulator. The temperature difference between the hot side facing the sun and the cold side facing the telescope is about 300 degrees Celsius, one of the largest temperature gradients maintained by any human-made object. The shape and positioning of the layers were carefully designed to radiate heat away into space. Each successive layer from the sun side to the telescope side is cooler than the one before it. The gaps between the layers allow heat to radiate out to the sides, preventing it from building up and eventually reaching the telescope. Special trim flaps on the sides can be adjusted to fine-tune the heat flow and keep the telescope at the optimal temperature. Webb carries 4 main scientific instruments, each designed for different types of observations, and all of them have proven invaluable for exoplanet science. The Near-Infrared Camera, or NIR-CAM, is Webb's primary imager. It can take pictures at wavelengths from 0.6 to 5 micrometers, covering the range from red visible light through the near-infrared. NIR-CAM has been essential for direct imaging of exoplanets, capturing actual pictures of planets orbiting other stars, something that was barely possible with previous telescopes. The Near-Infrared Spectrograph, or NIR-SPEC, can split infrared light into its component wavelengths to create spectra. This is crucial for analyzing exoplanet atmospheres. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere. Different molecules in the atmosphere absorb light at specific wavelengths, creating a fingerprint that NIR-SPEC can read. NIR-SPEC has a revolutionary feature called a microshutter array, containing about 250,000 tiny shutters that can be opened or closed individually. This allows NIRSpec to observe up to 200 objects simultaneously, dramatically increasing its efficiency. The Mid-Infrared Instrument, or MIRI, observes at longer infrared wavelengths from 5 to 28 micrometers. This is where planets emit most of their thermal radiation, making MIRI essential for studying planet temperatures and heat distribution. MIRI requires additional cooling beyond what the sunshield provides, using a special cryocooler to reach 7 Kelvin, just 7 degrees above absolute zero. This extreme cooling allows MIRI to detect incredibly faint heat signatures from distant planets. The Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph, or FGS/NIRIS, serves a dual purpose. The FGS keeps the telescope pointed precisely at its target, essential for the long observations needed to study exoplanets. NIRIS can perform specialized spectroscopic observations, including a mode specifically designed for studying exoplanet atmospheres during transits. One of Webb's most important capabilities for exoplanet science is its incredible stability. When observing a transit, where a planet passes in front of its star, the telescope needs to measure tiny changes in the star's brightness, sometimes less than 100 parts per million. Any jitter or drift in the telescope's pointing would add noise to these measurements. Webb's reaction wheels and fine guidance system can keep the telescope steady to within a few milliarcseconds, about the width of a human hair seen from 40 kilometers away. The telescope's location also contributes to its stability and sensitivity. Webb orbits the second Lagrange point, or L2, about 1.5 million kilometers from Earth in the direction away from the Sun. This special point in space moves around the Sun with Earth, keeping the Sun, Earth, and Moon all in the same direction from the telescope. This means the sun shield can continuously block their heat and light, allowing for uninterrupted observations. The environment at L2 is also very stable, with minimal gravitational perturbations that could affect the telescope's orbit or pointing. The journey to L2 took about a month after launch, during which Webb underwent one of the most complex deployment sequences ever attempted in space. The telescope launched folded up like origami, and over the course of 2 weeks, it unfolded itself through more than 300 single-point-of-failure deployments. The sunshield alone involved 140 release mechanisms, 70 hinge assemblies, 400 pulleys, and 90 cables. The fact that this all worked flawlessly is a testament to the years of testing and preparation that went into the mission. Webb's communication system allows it to send vast amounts of data back to Earth. The telescope can transmit data at up to 28 megabits per second through its high-gain antenna, which always points toward Earth. This high data rate is essential for exoplanet observations, which often involve taking thousands of images or spectra over many hours to track how a planet's signal changes over time. The telescope's onboard computer systems are sophisticated enough to execute complex observation sequences autonomously. For many exoplanet observations, timing is critical. A transit might last only a few hours and occur at a specific, predictable time. Webb's systems can be programmed to execute these observations precisely, adjusting the telescope's pointing, configuring the instruments, and taking data at exactly the right moments. The moment when the James Webb Space Telescope opened its eye to the universe for the first time marked the beginning of a new era in astronomy. After decades of planning, construction, and a nail-biting launch and deployment, the telescope was finally ready to begin its scientific mission. The first images released to the public in July of 2022 captured the world's imagination, but for exoplanet scientists, the real excitement was in the data that started flowing in from Webb's first observations of worlds beyond our solar system. Even before the official start of science operations, during the commissioning phase when engineers were still testing and calibrating the instruments, Webb demonstrated its extraordinary capabilities for exoplanet science. One of the first exoplanets Webb observed was HAT-P18b, a gas giant planet about the mass of Saturn orbiting close to its star. This observation was primarily a test to see how well Webb could measure the tiny dimming of starlight as a planet passes in front of its star. The results exceeded expectations. Webb measured the transit with a precision of just 20 parts per million, about 10 times better than what ground-based telescopes could achieve. But the observation that really announced Webb's arrival as a revolutionary tool for exoplanet science was its study of WASP 96b, one of the first 5 showcase observations released to the public. This planet is a hot gas giant about half the mass of Jupiter, orbiting its star every 3.5 days. Webb's near-infrared imager and slitless spectrograph captured the most detailed spectrum ever taken of an exoplanet atmosphere, revealing the unmistakable signature of water vapor along with evidence of hazes and clouds. What made this observation so remarkable wasn't just the detection of water, which had been seen in exoplanet atmospheres before, but the incredible detail and precision of the measurement. The spectrum showed not just that water was present, but revealed the shape of the water absorption features with such clarity that scientists could begin to infer the temperature structure of the atmosphere and the presence of clouds at different altitudes. It was like going from a blurry photograph to a high-definition image, suddenly able to see details that were completely invisible before. The early months of Webb's operations saw a parade of groundbreaking observations that demonstrated the telescope's versatility in studying different types of exoplanets. One particularly exciting early target was the TRAPPIST-1 system, a remarkable collection of 7 Earth-sized planets orbiting a small, cool red dwarf star just 39 light-years from Earth. This system had been discovered in 2017 and immediately became one of the most studied exoplanet systems because several of its planets orbit in the star's habitable zone, where liquid water could potentially exist on their surfaces. Webb's first look at TRAPPIST-1b, the innermost planet in the system, used the mid-infrared instrument to measure the heat coming from the planet's dayside. By observing the system just before and after the planet passed behind its star, an event called a secondary eclipse, Webb could measure how much infrared light was coming from the planet itself. The observations revealed that TRAPPIST-1b has a dayside temperature of about 500 Kelvin, or 230 degrees Celsius, hot enough to melt lead. This measurement was precise enough to rule out a thick atmosphere on this planet, as an atmosphere would redistribute heat from the dayside to the nightside, resulting in a lower dayside temperature than what was observed. Another early triumph came from observations of the gas giant WASP-39b, located about 700 light-years from Earth. Webb's near-infrared spectrograph obtained a transmission spectrum of this planet's atmosphere with unprecedented detail, revealing a complex chemical composition. The observations detected not just water vapor, but also carbon dioxide, carbon monoxide, sodium, and potassium. Most excitingly, this was the first time carbon dioxide had been definitively detected in an exoplanet atmosphere, a molecule that's particularly important because it's one of the main components of the atmospheres of Venus and Mars in our own solar system. The detection of carbon dioxide was a crucial demonstration of Webb's unique capabilities. This molecule has its strongest absorption feature at 4.5 micrometers, a wavelength that's impossible to observe from the ground because Earth's own atmosphere absorbs light at this wavelength. Previous space telescopes like Hubble couldn't observe this wavelength either, as they weren't designed for mid-infrared observations. Only Webb, with its infrared-optimized design and location beyond Earth's atmosphere, could make this detection. The precision of Webb's measurements also allowed scientists to detect more subtle atmospheric phenomena. In the atmosphere of WASP-39b, they found evidence of sulfur dioxide, a molecule that forms through photochemistry, similar to how ozone forms in Earth's atmosphere. This was the first detection of photochemistry in an exoplanet atmosphere, showing that these distant worlds have active atmospheric processes driven by their stars' radiation. One of the most ambitious early observations targeted the planet K2-18b, a subneptune about 120 light-years from Earth that orbits in its star's habitable zone. This planet had attracted attention because previous observations with Hubble had detected water vapor in its atmosphere, raising the possibility that it might have conditions suitable for life. Webb's observations revealed a much more complex picture. The telescope detected not only water vapor but also methane and possibly dimethyl sulfide, a molecule that on Earth is primarily produced by living organisms. However, the presence of these molecules doesn't necessarily mean there's life on K2-18b. The planet is much larger than Earth, somewhere between the size of Earth and Neptune, and likely has a thick hydrogen-rich atmosphere that would create conditions very different from anything on Earth. The detection of methane and other molecules could be explained by non-biological chemical processes in this alien environment. Still, the observation demonstrated Webb's ability to detect a wide range of molecules that could, in the right context, be biosignatures. Webb also turned its gaze to some of the most extreme exoplanets known. The ultra-hot Jupiter WASP 18b, with a dayside temperature exceeding 2700 Kelvin, provided a natural laboratory for studying atmospheric physics under extreme conditions. Webb created a temperature map of the planet's atmosphere, showing how heat is distributed from the scorching dayside to the cooler nightside. The observations revealed that the planet's atmosphere has strong winds that partially redistribute heat, but not as efficiently as in cooler gas giants, providing insights into how atmospheric dynamics change with temperature. Direct imaging of exoplanets, actually taking pictures of planets orbiting other stars, had always been one of the most challenging goals in exoplanet science. The overwhelming brightness of stars makes it nearly impossible to see planets orbiting close to them. But Webb's coronagraphs, devices that block out starlight to reveal faint objects nearby, combined with its infrared sensitivity and high resolution, opened new possibilities for direct imaging. One of Webb's first direct imaging successes was HIP 65426b, a gas giant planet about 7 times the mass of Jupiter orbiting a young star. Webb not only captured an image of this planet but obtained a spectrum of its light, revealing the composition of its atmosphere. The observations showed that this planet has a very different composition than expected based on models of planet formation, with less carbon relative to oxygen than predicted, challenging our understanding of how giant planets form. Perhaps even more impressive was Webb's direct imaging of the debris disk and exoplanets around the star HR 8799, better known as Fomalhaut. This nearby star, visible to the naked eye in the constellation Piscis Austrinus, is surrounded by a complex system of dusty debris disks, the remnants of planet formation. Webb's images revealed structure in these disks that had never been seen before, including gaps and rings that suggest the presence of unseen planets gravitationally sculpting the dust. The early observations also demonstrated Webb's ability to study planets around very different types of stars. Red dwarf stars, also called M-dwarfs, are the most common type of star in our galaxy, making up about 75% of all stars. These stars are much smaller and cooler than our Sun, and planets in their habitable zones orbit much closer to the star. This makes them easier to study with the transit method, as the planets orbit quickly and block a larger fraction of the star's light. Webb observed LHS 475b, a rocky planet slightly larger than Earth orbiting a red dwarf star. The observations showed that this planet likely lacks a significant atmosphere, similar to Mercury in our solar system. This was important because there's been a long-standing question about whether planets around red dwarf stars can maintain atmospheres. Red dwarfs are known to have powerful stellar flares that could strip away planetary atmospheres, especially for close-in planets. Webb's ability to determine whether these planets have atmospheres is crucial for understanding their potential habitability. The variety of observation modes available to Webb proved invaluable in these early studies. Transit spectroscopy, where the telescope observes starlight filtering through a planet's atmosphere, revealed atmospheric composition. Eclipse spectroscopy, observing the planet's own thermal emission, provided temperature measurements. Phase curves, tracking how a planet's brightness changes as it orbits its star, revealed information about atmospheric dynamics and heat distribution. Each technique provided different pieces of the puzzle, and Webb could employ all of them with unprecedented precision. One unexpected early discovery came from observations of the brown dwarf VHS 1256b. Brown dwarfs are objects that are too large to be planets but too small to be stars, occupying a middle ground between the two. Webb detected silicate clouds in this object's atmosphere, clouds made of tiny grains of sand. The observations revealed that these sand clouds are constantly forming and dissipating as material cycles through different layers of the atmosphere, creating a dynamic, ever-changing weather system unlike anything in our solar system. The ability to analyze the atmospheres of planets light years away from Earth represents one of the most remarkable achievements in modern astronomy. With the James Webb Space Telescope, we've entered an era where we can not only detect the presence of atmospheres around distant worlds but decode their chemical composition, temperature structure, and dynamic processes with extraordinary detail. This capability transforms exoplanets from simple points of light into complex worlds with their own weather, chemistry, and potentially even biochemistry. Understanding how Webb reads atmospheric chemistry requires appreciating the elegant physics behind spectroscopy. When light passes through a gas, molecules in that gas absorb specific wavelengths of light corresponding to their molecular structure. Each molecule has a unique pattern of absorption, like a fingerprint, that allows scientists to identify its presence. When starlight filters through a planet's atmosphere during a transit, it picks up these molecular fingerprints. By spreading this light into a spectrum and looking for these telltale absorption features, Webb can identify what molecules are present and in what abundances. The challenge is that these signals are incredibly faint. The atmosphere of an Earth-sized planet might absorb only a few hundred parts per million of the star's light, and the molecular features might change the absorption by only tens of parts per million. Detecting such tiny signals requires not just a large telescope to collect enough light, but also exquisite stability to measure these minute changes accurately. Webb achieves this through a combination of its large mirror, stable platform, and sophisticated instruments designed specifically for this type of measurement. One of Webb's most significant atmospheric discoveries has been the widespread presence of clouds and hazes in exoplanet atmospheres. These aerosols, tiny particles suspended in the atmosphere, had been suspected in many exoplanets based on previous observations, but Webb has revealed their nature and composition in unprecedented detail. In hot Jupiters, Webb has detected clouds made of exotic materials that would seem like science fiction if we hadn't observed them directly. There are clouds of liquid iron droplets in ultra-hot atmospheres where temperatures exceed 2000 Kelvin. There are clouds of silicate particles, essentially vaporized rock, that condense in slightly cooler atmospheres. And in even cooler atmospheres, Webb has found evidence of clouds made of more familiar substances like water ice and ammonia. The presence and properties of these clouds profoundly affect a planet's climate and appearance. Clouds can reflect starlight, cooling a planet's dayside. They can trap heat, warming a planet's nightside. They can obscure lower atmospheric layers, making it difficult to determine what lies beneath. Webb's ability to peer through these clouds using different wavelengths of infrared light has been crucial for understanding the full atmospheric structure of these worlds. The chemistry Webb has revealed in exoplanet atmospheres tells stories about how these planets formed and evolved. The ratio of carbon to oxygen in a planet's atmosphere, for instance, provides clues about where in the protoplanetary disk the planet formed. Planets that formed beyond the snow line, where water ice could condense, should have different carbon-to-oxygen ratios than those that formed closer to their star. Webb's precise measurements of molecules like water, carbon dioxide, carbon monoxide, and methane allow scientists to determine these ratios and trace a planet's formation history. In the atmosphere of WSP 18b, one of the hottest exoplanets known, Webb detected carbon monoxide but no sign of water vapor. This unusual chemistry results from the extreme temperature, which causes water molecules to break apart into hydrogen and oxygen atoms. The oxygen then combines with carbon to form carbon monoxide. This type of thermal dissociation only occurs at temperatures above about 2500 Kelvin, demonstrating how extreme conditions create chemistry unlike anything we see in our solar system. Webb has also revealed the three-dimensional structure of exoplanet atmospheres. By observing planets at different phases of their orbit, the telescope can map how temperature and composition vary with altitude, latitude, and longitude. These observations have shown that many hot Jupiters have strong temperature inversions, where the atmosphere gets hotter with altitude instead of cooler. This happens when molecules high in the atmosphere absorb starlight and heat up, similar to how ozone creates a temperature inversion in Earth's stratosphere. The dynamics of exoplanet atmospheres, how gases move and mix, have been another area where Webb has provided groundbreaking insights. In tidally locked planets, which always show the same face to their star, there's a permanent day side and night side. Webb has observed how powerful winds, sometimes exceeding 5,000 km per hour, transport heat from the scorching day side to the frigid night side. These winds create complex patterns of circulation that affect cloud formation, chemistry, and the overall climate of the planet. One particularly fascinating discovery has been the detection of photochemistry in exoplanet atmospheres. Just as sunlight drives chemical reactions in Earth's atmosphere, creating ozone and other photochemical products, stellar radiation drives chemistry in exoplanet atmospheres. Webb detected sulfur dioxide in the atmosphere of WSP 39b, a molecule that forms when hydrogen sulfide is broken apart by ultraviolet light and the sulfur combines with oxygen. This was the first detection of photochemistry in an alien atmosphere, showing that these distant worlds have active, dynamic atmospheres with complex chemical processes. The search for biosignatures, molecules that could indicate the presence of life, has been one of the most exciting aspects of Webb's atmospheric studies. While we haven't found definitive evidence of life yet, Webb has demonstrated its ability to detect many of the molecules that could be biosignatures in the right context. Methane, for instance, is produced by life on Earth, though it can also be produced by geological processes. Webb has detected methane in several exoplanet atmospheres, including the intriguing subneptune K2-18b, which orbits in its star's habitable zone. The detection of dimethyl sulfide in K2-18b's atmosphere was particularly intriguing because on Earth, this molecule is almost exclusively produced by marine phytoplankton. However, scientists are careful to note that we don't yet understand all the ways this molecule could be produced in an alien environment, especially one as different from Earth as K2-18b appears to be. The planet's thick hydrogen-rich atmosphere and high pressure would create conditions completely unlike anything on Earth, making it difficult to interpret potential biosignatures. Webb's observations have also revealed how stellar radiation shapes planetary atmospheres. Stars emit not just visible light but also ultraviolet and X-ray radiation that can profoundly affect planetary atmospheres. This high-energy radiation can break apart molecules, drive chemical reactions, and even strip away atmospheric gases entirely. Webb has observed the effects of this radiation on planets orbiting different types of stars, from sun-like stars to red dwarfs to hot, massive stars. Red dwarf stars, which make up the majority of stars in our galaxy, present particular challenges for planetary atmospheres. These stars are prone to powerful flares that blast their planets with intense radiation. Webb has studied several planets orbiting red dwarfs to understand how they respond to this harsh environment. Some planets appear to have lost their atmospheres entirely, becoming bare rocks like Mercury. Others have retained thick atmospheres, possibly protected by strong magnetic fields or constantly replenished by volcanic outgassing. The temperature structure of exoplanet atmospheres has proven to be far more complex than simple models predicted. Webb's observations have revealed that many planets have strong day-night temperature contrasts, vertical temperature gradients, and even seasonal variations. In the ultra-hot Jupiter KLT9b, the day side is so hot that molecules are torn apart into their constituent atoms, while the night side is cool enough for molecules to reform. This creates a chemical gradient across the planet, with different compositions on the day and night sides. Webb has also studied how clouds form and evolve in exoplanet atmospheres. The telescope's ability to observe at multiple wavelengths allows it to probe different altitude levels in an atmosphere, revealing where clouds form and what they're made of. In some planets, Webb has observed clouds forming on the night side and evaporating on the day side, creating a cycle of condensation and evaporation that transports material and energy through the atmosphere. The role of atmospheric escape, where gases are lost to space, has been another area where Webb has provided new insights. Many exoplanets, especially those orbiting close to their stars, are losing their atmospheres at prodigious rates. Webb can detect the extended atmospheres or exospheres of these planets, regions where gases are escaping to space. These observations help scientists understand how planetary atmospheres evolve over time and why some planets retain their atmospheres while others lose them. One of the most surprising discoveries has been the diversity of atmospheric compositions among seemingly similar planets. Planets of similar size, temperature, and stellar environment can have vastly different atmospheric compositions, suggesting that factors like formation history, impact events, and magnetic fields play crucial roles in determining a planet's atmospheric makeup. This diversity means that each new planet Webb observes has the potential to surprise us with unexpected chemistry or physics. Webb's observations have also revealed the importance of atmospheric dynamics in shaping a planet's observable properties. Winds, storms, and circulation patterns affect how heat and chemicals are distributed through an atmosphere. In some hot Jupiters, Webb has observed evidence of atmospheric waves, large-scale oscillations that transport energy and momentum. These waves can affect cloud formation, chemical reactions, and the overall energy balance of the planet. The precision of Webb's measurements has allowed scientists to detect trace gases that make up only tiny fractions of planetary atmospheres. These trace gases can be incredibly important for understanding atmospheric processes. For instance, the detection of sulfur compounds in minute quantities has revealed the presence of photochemistry that wouldn't be apparent from major atmospheric constituents alone. Webb has also begun to probe the atmospheres of smaller, rocky planets, though these observations are much more challenging than for gas giants. Rocky planets have thinner atmospheres that produce weaker signals, and many may have no atmosphere at all. Webb's observations of the TRAPPIST-1 system have been particularly important in this regard, as this system contains 7 Earth-sized planets that provide a natural laboratory for comparative planetology. The observations of TRAPPIST-1b and c have shown that these innermost planets likely lack thick atmospheres, possibly due to stellar radiation stripping them away. However, the outer planets in the system, which receive less stellar radiation, may have retained their atmospheres. Webb continues to observe these planets, building up a picture of how atmospheric retention varies with distance from the star. The study of atmospheric chemistry has also provided insights into planetary interiors. The gases in a planet's atmosphere must come from somewhere, either from the original protoplanetary disk, from outgassing from the interior, or from external sources like cometary impacts. By measuring atmospheric composition, Webb can constrain models of planetary interiors and evolution. For instance, the detection of volcanic gases would indicate an active interior, while the presence of noble gases could reveal information about a planet's formation. Webb's atmospheric studies have also revealed the importance of photochemical hazes, complex organic molecules that form when simpler molecules are broken apart and recombine under stellar radiation. These hazes can significantly affect a planet's climate by absorbing or scattering light. In some cases, hazes can create a greenhouse effect, warming the planet. In others, they can reflect light, cooling it. Webb's ability to characterize these hazes helps scientists understand their role in planetary climates. The quest to find planets similar to Earth has captivated humanity since we first realized that other worlds might exist beyond our solar system. These rocky planets, with solid surfaces where one might stand and look up at alien skies, represent our best hope for finding life as we know it. The James Webb Space Telescope has revolutionized our ability to study these small, rocky worlds, revealing their nature in detail that was impossible just a few years ago. Rocky planets, also called terrestrial planets, are fundamentally different from the gas giants that were the first exoplanets discovered. While gas giants are massive balls of hydrogen and helium with no solid surface, rocky planets are made primarily of heavier elements like silicon, iron, magnesium, and oxygen, formed into minerals and rocks. In our solar system, Mercury, Venus, Earth, and Mars are the rocky planets, each with its own unique characteristics despite their similar compositions. Finding and studying rocky exoplanets is extraordinarily challenging. They're much smaller than gas giants, typically having radii less than twice Earth's radius. When they transit their star, they block much less light, making them harder to detect. Their atmospheres, if they have them at all, are much thinner than those of gas giants, producing weaker spectroscopic signals. And because they're less massive, they cause smaller wobbles in their star's motion, making them difficult to detect with the radial velocity method. Despite these challenges, astronomers had discovered thousands of rocky planet candidates before Webb's launch, primarily thanks to the Kepler Space Telescope. But Kepler could only determine these planets' sizes and orbital periods. To understand what these worlds are really like, whether they have atmospheres, whether they might be habitable, required the kind of detailed observations that only Webb can provide. One of Webb's primary targets for rocky planet observations has been the TRAPPIST-1 system, that remarkable collection of 7 Earth-sized planets orbiting a red dwarf star. This system is like a cosmic laboratory for studying rocky planets, with worlds ranging from scorching hot to potentially habitable, all orbiting the same star. By comparing these planets, scientists can understand how factors like stellar radiation and orbital distance affect planetary evolution. Webb's observations of TRAPPIST-1b, the innermost planet, revealed a world very different from Earth. Using the mid-infrared instrument, Webb measured the planet's thermal emission and found a dayside temperature of about 500 Kelvin. This temperature measurement was precise enough to determine that the planet lacks a substantial atmosphere. If it had a thick atmosphere, winds would transport heat from the dayside to the nightside, lowering the observed dayside temperature. The absence of this cooling effect indicates that TRAPPIST-1b is likely a bare rock, similar to Mercury in our solar system. The second planet, TRAPPIST-1c, told a similar story. Webb's observations showed that it too lacks a thick atmosphere, with a dayside temperature consistent with bare rock or perhaps a very thin atmosphere of carbon dioxide. These results were somewhat disappointing for those hoping to find Earth-like atmospheres, but they're scientifically valuable. They tell us that planets orbiting very close to red dwarf stars face challenges in maintaining atmospheres, possibly due to stellar flares and intense ultraviolet radiation. But the TRAPPIST-1 system still holds promise. The outer planets, particularly TRAPPIST-1e, F, and G, orbit in or near the star's habitable zone, where temperatures could allow liquid water on their surfaces. These planets receive less stellar radiation and may have been able to retain their atmospheres. Webb continues to observe these worlds, slowly building up the signal needed to detect and characterize any atmospheres they might have. Another rocky world that Webb has studied intensively is LHS 475b, a planet almost exactly the same size as Earth orbiting a red dwarf star 41 light-years away. This was actually the first exoplanet confirmed by Webb, demonstrating the telescope's ability to detect and study Earth-sized worlds. The planet orbits its star in just 2 days, making it far too hot for life as we know it, but it serves as an important test case for understanding rocky planets around red dwarfs. Webb's observations have shown that LHS 475b could have no atmosphere, like TRAPPIST-1b, or it could have a pure carbon dioxide atmosphere, like Venus. Distinguishing between these possibilities requires more observations, but the fact that Webb can even pose this question for an Earth-sized planet 41 light-years away is remarkable. Each observation adds another piece to the puzzle, gradually revealing the nature of this distant world. The search for truly Earth-like planets, worlds with nitrogen-oxygen atmospheres, liquid water, and perhaps even life, remains one of Webb's ultimate goals. These planets are incredibly difficult to study because they're small, their atmospheres produce weak signals, and they orbit in their star's habitable zone, meaning they take months or years to complete an orbit. This makes it challenging to observe multiple transits, which are needed to build up enough signal to detect atmospheric features. Webb has begun observing some of the most promising potentially habitable rocky planets. LP8909c, also known as TOI732c, is a super-Earth about 1.5 times the size of Earth that orbits in its star's habitable zone. While larger than Earth, it's still likely to be a rocky planet, and its temperature could allow liquid water on its surface. Webb's observations are searching for signs of an atmosphere and, if one exists, determining its composition. The concept of the habitable zone, the region around a star where liquid water could exist on a planet's surface, has been refined by Webb's observations. The traditional habitable zone assumes a planet with an Earth-like atmosphere, but Webb has shown that atmospheric composition dramatically affects a planet's surface temperature. A thick carbon dioxide atmosphere can warm a planet through the greenhouse effect, extending the habitable zone outward. Conversely, a thin atmosphere or no atmosphere at all means a planet needs to be closer to its star to maintain liquid water. Webb has also studied super-Earths, planets larger than Earth but smaller than Neptune. These planets don't exist in our solar system, but they're common around other stars. Their nature has been a mystery. Are they large rocky planets, small gas planets, or something in between? Webb's observations are helping to answer this question by measuring their densities and atmospheric compositions. The planet TOI270b, about 1.5 times the size of Earth, has been a particularly interesting super-Earth for Webb to study. Observations have revealed that this planet has an atmosphere, but not the hydrogen-rich atmosphere of a mini-Neptune. Instead, it might have a heavier atmosphere made of water vapor, methane, or carbon dioxide. This suggests that TOI270b is indeed a large rocky planet rather than a small gas planet, helping to define the boundary between these two types of worlds. Webb's study of rocky planets has also revealed the importance of planetary geology in shaping atmospheres. Volcanic activity can replenish gases lost to space, maintaining an atmosphere over billions of years. Webb has searched for signs of volcanism on exoplanets by looking for volcanic gases like sulfur dioxide and hydrogen sulfide. While no definitive detection of exoplanet volcanism has been made yet, Webb's continued observations may eventually reveal volcanically active worlds. The interaction between stellar radiation and planetary surfaces is another area where Webb has provided new insights. On airless worlds, the surface is directly exposed to stellar radiation, which can alter minerals and create thin exospheres of atoms sputtered from the surface. Webb can detect these exospheres, providing information about surface composition and the effects of space weathering. Webb has also begun to study rocky planets around Sun-like stars, though these observations are even more challenging than for planets around red dwarfs. Planets in the habitable zones of Sun-like stars have orbital periods of months to years, making it difficult to observe multiple transits. Additionally, Sun-like stars are brighter than red dwarfs, making it harder to detect the tiny signals from transiting rocky planets. Despite these challenges, Webb has observed some rocky planets around Sun-like stars. HD 219134b, slightly larger than Earth, orbits a star similar to our Sun. While this planet orbits too close to its star to be habitable, studying it helps scientists understand how rocky planets around Sun-like stars differ from those around red dwarfs. The diversity of rocky planets revealed by Webb has been striking. Some are airless balls of rock and metal. Others have thick, toxic atmospheres. Some are locked in eternal day and night, while others rotate like Earth. This diversity suggests that the path to creating an Earth-like planet is narrow, requiring just the right combination of size, composition, stellar environment, and evolutionary history. Webb's observations have also highlighted the importance of planetary magnetic fields, though these can't be directly detected with current technology. Magnetic fields can protect atmospheres from stellar wind erosion, particularly important for planets around active red dwarf stars. Planets that have lost their magnetic fields, perhaps due to cooling interiors, may have also lost their atmospheres. The presence or absence of atmospheres on otherwise similar planets may indicate which worlds have protective magnetic fields. The study of rocky exoplanets has implications beyond the search for life. These worlds serve as laboratories for understanding planetary physics under conditions we can't replicate on Earth. Planets with surface temperatures exceeding 1000 Kelvin show us how rocks behave when they're partially molten. Planets with pure carbon dioxide atmospheres help us understand greenhouse effects more extreme than anything in our solar system. Each world teaches us something new about the possible outcomes of planetary evolution. The gas giants of our solar system, Jupiter and Saturn with their swirling clouds and dozens of moons, have long fascinated astronomers. But the gas giants orbiting other stars have proven to be far more diverse and extreme than anything in our cosmic neighborhood. Webb's unprecedented ability to peer into the atmospheres of these massive worlds has revealed compositions, structures, and processes that challenge our understanding of planetary physics and chemistry. Gas giants are fundamentally different from rocky planets in almost every way. They formed from the accumulation of hydrogen and helium gas in the protoplanetary disk, growing massive enough that their gravity could hold on to these light elements that escape from smaller planets. Their enormous size, typically 10 to 20 times the diameter of Earth or larger, means they have no solid surface as we understand it. Instead, their atmospheres gradually transition to liquid and then possibly solid states under the crushing pressure of their interiors. The first exoplanets discovered around Sun-like stars were gas giants, but they were nothing like Jupiter or Saturn. These hot Jupiters orbit their stars in just a few days, their atmospheres heated to temperatures that would melt iron. Webb has studied these extreme worlds in exquisite detail, revealing atmospheric compositions and dynamics that push the boundaries of what we thought was possible. WSP-18b exemplifies these extreme worlds. This planet, about 10 times the mass of Jupiter, orbits its star in less than a day. The same side always faces the star, creating a permanent day side with temperatures exceeding 2700 Kelvin and a night side that's more than 1000 degrees cooler. Webb's observations revealed that the day side is so hot that water molecules are torn apart into hydrogen and oxygen atoms. The oxygen then combines with carbon to form carbon monoxide, creating an atmosphere dominated by this molecule rather than the water vapor we might expect. The temperature map Webb created of WSP-18b's atmosphere showed remarkable structure. The hottest point isn't directly under the star but shifted eastward by powerful winds. These winds, moving at speeds of several kilometers per second, are driven by the enormous temperature difference between day and night. But unlike cooler gas giants where winds efficiently redistribute heat, WSP-18b's winds only partially mix the day and night sides, maintaining an extreme temperature gradient. Webb has also studied cooler gas giants that more closely resemble Jupiter and Saturn, though even these worlds often have surprising compositions. WSP-80b, a warm gas giant with a temperature around 800 Kelvin, showed a rich spectrum of molecules including water vapor, methane, and carbon dioxide. But the relative abundances of these molecules didn't match predictions based on solar system gas giants. This planet has less methane than expected for its temperature, suggesting either a different formation history or atmospheric processes we don't yet understand. The diversity of gas giant compositions has been one of Webb's most important discoveries. Classical models of planet formation predicted that gas giants should have compositions similar to their host stars, perhaps slightly enriched in heavy elements. But Webb has found planets with carbon-to-oxygen ratios very different from their stars, suggesting that the simple picture of planets inheriting their star's composition is incomplete. The case of VHS 1256b, a massive companion to a brown dwarf, illustrated just how exotic gas giant atmospheres can be. Webb detected clouds of silicate particles in this object's atmosphere, essentially clouds made of tiny grains of sand. The temperature, about 1100 Kelvin, is just right for silicate clouds to form. These sand particles constantly form, grow, and rain out of the observable atmosphere, creating a dynamic weather system unlike anything in our solar system. Webb's ability to observe in the infrared has been crucial for understanding gas giant compositions. Many important molecules, particularly those containing carbon, have their strongest features in the infrared. Methane, ethane, and other hydrocarbons that are important in gas giant atmospheres are nearly invisible to optical telescopes but stand out clearly in Webb's infrared observations. The vertical structure of gas giant atmospheres, how temperature and composition change with altitude, has been another area where Webb has excelled. By observing at different wavelengths, Webb can probe different depths in an atmosphere. Shorter wavelengths tend to probe higher altitudes while longer wavelengths can penetrate deeper. This tomographic approach has revealed that many gas giants have complex vertical structures with multiple cloud layers, temperature inversions, and chemical gradients. In the atmosphere of WSP-39b, Webb detected not just the presence of clouds but their vertical distribution. High-altitude clouds of exotic compositions scatter light at short wavelengths, while deeper clouds of different compositions affect longer wavelengths. The interplay between these cloud layers affects the planet's energy balance and observable properties in complex ways that we're only beginning to understand. The discovery of photochemistry in gas giant atmospheres has been one of Webb's most significant contributions. In WSP-39b, Webb detected sulfur dioxide, a molecule that forms when hydrogen sulfide is broken apart by ultraviolet light and the sulfur combines with oxygen. This photochemical process is similar to how ozone forms in Earth's atmosphere, but it occurs under very different conditions. The detection of photochemistry shows that gas giant atmospheres are not just passive mixtures of gases but active chemical systems driven by their star's energy. Webb has also studied gas giants at a wide range of distances from their stars, from hot Jupiters that nearly touch their stars to cold giants in wide orbits. This diversity has revealed how stellar radiation shapes atmospheric chemistry. Close-in planets are dominated by carbon monoxide and other high-temperature molecules. At intermediate distances, methane becomes important. Far from their stars, ammonia and other molecules that would be destroyed by stellar radiation can survive. The planet WSP-107b provided a particularly interesting case study in atmospheric dynamics. This planet has one of the most inflated atmospheres known, with a density less than that of Cork. Webb's observations revealed that this inflation might be caused by tidal heating, where the star's gravity flexes the planet and generates internal heat. This process, similar to what powers volcanism on Jupiter's moon Io, could explain why some gas giants are much larger than models predict. Webb's direct imaging capabilities have allowed it to study gas giants that orbit far from their stars, worlds that are impossible to detect with the transit method. HIP 65426b, imaged directly by Webb, orbits its star at a distance about 100 times greater than Earth orbits the Sun. At this enormous distance, the planet takes hundreds of years to complete a single orbit, making transit observations impossible. But Webb can see the planet's infrared glow directly, separate from its star's light, and analyze its atmosphere through the light the planet itself emits. The spectrum Webb obtained from this distant world revealed something unexpected. The planet's atmosphere contains carbon monoxide but shows unusually low amounts of methane, suggesting a carbon-to-oxygen ratio very different from what models of planet formation predicted. This discovery challenges our understanding of how giant planets form in the outer regions of planetary systems. If planets form by accumulating solid material and gas from the surrounding disk, their composition should reflect the composition of that disk. But HIP 65426b's unusual chemistry suggests either our models of disk chemistry are incomplete, or this planet formed through a different mechanism than we expected. The study of atmospheric chemistry becomes even more intriguing when we consider smaller planets, the sub-Neptunes and super-Earths that have no analog in our solar system. These planets, with sizes between Earth and Neptune, are among the most common types of planets in the galaxy, yet we knew almost nothing about their atmospheres before Webb. The challenge with these smaller worlds is that their atmospheric signals are much weaker than those of giant planets. Their smaller size means they block less starlight during transits, and their lower mass means their atmospheres are more compact, creating weaker absorption features. Despite these challenges, Webb has made remarkable progress in characterizing these mysterious worlds. The planet TOI-270b, about 1.5 times the size of Earth, provided one of the first detailed looks at a super-Earth atmosphere. Webb's observations revealed an atmosphere dominated by water vapor and methane, with hints of carbon dioxide. The presence of these molecules suggests the planet has a hydrogen-rich atmosphere, more like a mini-Neptune than a scaled-up version of Earth. This finding contributes to the ongoing debate about the nature of these intermediate-sized planets and whether there's a clear dividing line between rocky super-Earths and gaseous mini-Neptunes. The temperature structure of exoplanet atmospheres has proven to be far more complex than simple models predicted. Webb's observations have revealed that many planets have strong day-night temperature contrasts, vertical temperature gradients, and hot spots that don't always appear where expected. The hot Jupiter WASP 43b, for instance, has a hot spot that's shifted eastward from the point directly facing the star, displaced by powerful winds that blow from west to east. Webb mapped the temperature across this planet's surface, showing variations of more than 600 degrees Kelvin between the hottest and coolest regions. These temperature maps tell us about more than just weather patterns. They reveal fundamental properties of atmospheric physics under extreme conditions. The efficiency of heat transport from day to night, for instance, depends on the atmospheric composition, the strength of winds, and the presence of clouds. By measuring these temperature distributions for planets with different compositions and irradiation levels, Webb is helping scientists understand how atmospheric dynamics scale with temperature, gravity, and other fundamental parameters. Chemical disequilibrium in exoplanet atmospheres has emerged as one of the most exciting areas of study. In thermochemical equilibrium, the abundances of different molecules are determined solely by temperature and pressure. But many exoplanet atmospheres show abundances that deviate from equilibrium, indicating that dynamic processes like vertical mixing or photochemistry are at work. These disequilibrium states are particularly interesting because on Earth, the most dramatic atmospheric disequilibrium, the coexistence of oxygen and methane, is maintained by life. Webb detected potential chemical disequilibrium in the atmosphere of K2-18b, where the simultaneous presence of methane, carbon dioxide, and possibly dimethyl sulfide suggests active chemical processes. While these particular combinations don't necessarily indicate biological activity, they demonstrate that exoplanet atmospheres are dynamic systems with complex chemistry that goes beyond simple equilibrium models. Understanding these disequilibrium states is crucial for interpreting potential biosignatures in the future. The role of stellar radiation in shaping atmospheric chemistry has become increasingly apparent through Webb's observations. Different types of stars emit different spectra of light, with consequences for planetary atmospheres. Red dwarf stars, for instance, emit less ultraviolet radiation than Sun-like stars, which affects photochemical reactions. But they also have more frequent and powerful flares that can drive chemistry through sudden bursts of high-energy radiation. Webb has observed how these different stellar environments create diverse atmospheric compositions even among otherwise similar planets. The planet LTT 9779b, orbiting a red dwarf star, provided a perfect example of how stellar radiation shapes atmospheric chemistry. This planet, only slightly larger than Earth, orbits so close to its star that it completes an orbit in just 24 hours. Webb's observations showed that the planet's dayside is hot enough to vaporize rock, creating an atmosphere of rock vapor that likely rains liquid rock on the nightside. The extreme stellar irradiation has completely transformed what might have once been a more Earth-like world into something utterly alien. Isotope ratios in exoplanet atmospheres represent another frontier that Webb has begun to explore. Different isotopes of the same element have Sly. The detection of deuterium, a heavy isotope of hydrogen, in exoplanet atmospheres has particular significance. The ratio of deuterium to regular hydrogen can reveal whether a planet has lost significant amounts of its atmosphere over time, as lighter hydrogen escapes to space more easily than heavier deuterium. Webb's measurements of this ratio in several exoplanets have shown that atmospheric escape is a common process, especially for planets orbiting close to their stars. Seasonal variations in exoplanet atmospheres present another layer of complexity that Webb has begun to uncover. While most of the hot Jupiters Webb observes are tidally locked and don't experience seasons like Earth, planets on eccentric orbits do experience dramatic changes in stellar heating as they move closer to and farther from their star. The planet HD 80307b, with an orbit as eccentric as a comet's, experiences temperature swings of over 1,000 degrees as it swoops close to its star and then retreats to colder distances. Webb has tracked how the atmosphere responds to these changes, revealing how clouds form and dissipate, how chemistry shifts between different states, and how winds reorganize in response to changing heating patterns. The interaction between atmospheres and planetary magnetic fields has also come into focus through Webb's observations. While the telescope can't directly detect magnetic fields, it can see their effects on atmospheric chemistry and structure. Auroras, caused by charged particles interacting with magnetic fields, can drive unusual chemistry in the upper atmosphere. Webb has detected what might be auroral emissions from several gas giant exoplanets, suggesting these worlds have magnetic fields that protect their atmospheres from stellar wind erosion. One of the most ambitious goals for atmospheric studies is to detect and characterize the atmospheres of potentially habitable worlds. These Earth-sized planets in the habitable zones of their stars represent the holy grail of exoplanet science. The challenge is immense. Their atmospheres produce signals that are barely above the noise level even for Webb. But the telescope has made promising initial observations. The TRAPPIST-1 system, with its 7 Earth-sized planets, has been a primary target for these studies. Webb's observations of TRAPPIST-1b and c have shown that these innermost planets likely lack thick atmospheres, possibly stripped away by their star's radiation. But the outer planets, especially TRAPPIST-1e, f, and g, which orbit in or near the habitable zone, remain promising targets. Webb continues to observe these worlds, slowly building up the signal needed to detect and characterize any atmospheres they might possess. The search for biosignatures, chemical signs of life, in exoplanet atmospheres represents one of Webb's most ambitious goals. While the telescope wasn't specifically designed to detect life, its capabilities make it possible to search for certain biosignature gases. Oxygen and methane together, for instance, would be a strong biosignature because these gases react with each other and shouldn't coexist without a source continuously producing them. On Earth, that source is life, photosynthesis producing oxygen and various organisms producing methane. Webb's observations have shown that detecting such biosignatures will be extremely challenging but not impossible. The key is to observe many transits of the same planet, building up signal over time, and to carefully model all possible non-biological sources of any detected gases. The telescope has already demonstrated it can detect methane, carbon dioxide, and water vapor in the atmospheres of small planets. Adding oxygen to this list would require even more sensitive observations, but it's within Webb's capabilities for the nearest Earth-sized planets. The study of atmospheric escape has revealed that many exoplanets are actively losing their atmospheres to space. This process, driven by stellar radiation and stellar wind, can completely transform a planet over billions of years. Webb has observed extended atmospheres and comet-like tails of escaping gas from several planets, particularly those orbiting close to their stars. The planet HAT P32b, for instance, is losing its atmosphere so rapidly that it will be completely stripped in a few billion years, leaving behind only its rocky core. Understanding atmospheric escape is crucial for assessing planetary habitability. Earth's magnetic field protects our atmosphere from the solar wind, but not all planets have such protection. Mars, for instance, lost most of its atmosphere billions of years ago, transforming from a potentially habitable world to the cold, dry planet we see today. Webb's observations of atmospheric escape from exoplanets help us understand how common this process is and what factors determine whether a planet can retain its atmosphere over geological timescales. The quest to find planets like our own Earth represents one of humanity's most profound scientific endeavors. These rocky worlds, with solid surfaces where water might pool into lakes and oceans, where continents might rise from ancient seas, and where the delicate chemistry of life might take hold, have captured our imagination and driven the search for exoplanets from the very beginning. With the James Webb Space Telescope, we've entered a new chapter in this search, one where we can not only find Earth-sized worlds but begin to understand their surfaces, atmospheres, and potential for harboring life. Rocky planets present unique challenges for observation. Unlike the giant planets with their extended, hydrogen-rich atmospheres that create strong spectroscopic signals, rocky worlds have compact atmospheres, if they have atmospheres at all. The signals we're trying to detect are often at the very limit of what's technically possible, requiring multiple observations and sophisticated analysis techniques to tease out the faint whispers of these distant worlds from the noise. The diversity of rocky exoplanets discovered by Webb has shattered any simple notions of what Earth-like might mean. These worlds range from airless rocks baked by their stars to planets shrouded in thick, crushing atmospheres, from worlds locked in eternal day and night to planets with surfaces of molten lava. Each discovery expands our understanding of how rocky planets form, evolve, and potentially develop conditions suitable for life. LHS 475b represents one type of rocky world that Webb has studied in detail. This planet, only slightly larger than Earth, orbits extremely close to its red dwarf star, completing an orbit in just 2 days. Webb's observations revealed that this world has no significant atmosphere, its surface directly exposed to the harsh radiation of its star. The dayside temperature reaches 700 Kelvin, hot enough to melt lead, while the nightside, receiving no stellar heating, plunges to near absolute zero. This extreme temperature contrast exists because there's no atmosphere to transport heat from day to night. The absence of an atmosphere on LHS 475b tells us something important about planetary evolution around red dwarf stars. These stars, which make up the majority of stars in our galaxy, are known for their violent flares and strong stellar winds, especially when they're young. The fact that LHS 475b lacks an atmosphere suggests that many rocky planets orbiting close to red dwarfs might have their atmospheres stripped away early in their history, limiting their potential for habitability. But not all rocky planets around red dwarfs are airless. Webb's observations of LTT 1445ab revealed a very different kind of world. This planet, about 1¼ times the size of Earth, appears to have an atmosphere, though not one that would be friendly to life as we know it. The spectroscopic data suggests an atmosphere dominated by carbon dioxide or carbon monoxide, with temperatures that would make the planet uninhabitable. Still, the mere presence of an atmosphere on a rocky planet orbiting a red dwarf is encouraging for the possibility of finding habitable worlds around these common stars. The concept of the habitable zone, the distance from a star where liquid water could exist on a planet's surface, has been refined and complicated by Webb's observations. The traditional definition assumed an Earth-like atmosphere, but Webb has shown that atmospheric composition dramatically affects a planet's surface temperature. A thick carbon dioxide atmosphere can warm a planet through the greenhouse effect, extending the habitable zone outward. Conversely, a thin atmosphere or one with high-altitude clouds that reflect sunlight could cool a planet, shrinking the habitable zone inward. Webb's study of TOI 715b illustrated this complexity. This planet orbits within what would traditionally be considered the habitable zone of its star, but Webb's observations revealed an atmosphere so thick and hot that any water on the surface would exist only as superheated steam. The planet appears to have a runaway greenhouse effect similar to Venus in our own solar system, demonstrating that location in the habitable zone doesn't guarantee habitable conditions. The search for truly Earth-like exoplanets has focused considerable attention on the TRAPPIST-1 system. This remarkable system contains 7 rocky planets, all roughly Earth-sized, orbiting an ultra-cool dwarf star. 3 of these planets, TRAPPIST-1e, F, and G, orbit within or near the habitable zone. Webb has conducted extensive observations of this system, slowly building up our understanding of each world. TRAPPIST-1b, the innermost planet, has been observed multiple times by Webb. The observations confirm that this world lacks a substantial atmosphere, with surface temperatures on the dayside reaching about 500 Kelvin. But the precision of Webb's measurements revealed something interesting. The planet's dayside is slightly cooler than expected for a bare rock, suggesting either some form of heat redistribution, possibly through a very thin atmosphere, or a surface with unusual properties that affect how it absorbs and emits radiation. TRAPPIST-1c, the second planet, tells a similar story but with intriguing differences. Webb's measurements suggest this planet might have a very thin atmosphere, perhaps dominated by carbon dioxide. The uncertainty in these measurements highlights the challenge of studying Earth-sized exoplanets. Even with Webb's unprecedented capabilities, detecting and characterizing the thin atmospheres of rocky worlds requires pushing the telescope to its absolute limits. The outer TRAPPIST-1 planets remain tantalizingly mysterious. These worlds, orbiting in or near the habitable zone, could potentially harbor liquid water on their surfaces if they have the right atmospheric conditions. Webb continues to observe these planets, with each transit adding a small amount of information to our growing dataset. It may take years of observations to definitively determine whether these worlds have atmospheres and what those atmospheres are made of, but the potential payoff, finding a potentially habitable world, makes the effort worthwhile. Beyond individual planets, Webb has revealed patterns in the population of rocky exoplanets that inform our understanding of planetary formation and evolution. One striking pattern is the radius valley, a deficit of planets with sizes between about 1.5 and 2 times Earth's radius. This gap appears to separate rocky super-Earths from gaseous subneptunes. Webb's ability to measure planetary masses through precise timing of transits, combined with radius measurements, has helped clarify this division. The radius valley likely results from atmospheric loss. Planets that start with hydrogen-helium atmospheres can lose these light gases to space, especially if they orbit close to their stars. Smaller planets, with weaker gravity, lose their atmospheres entirely, becoming bare rocky worlds. Larger planets retain some atmosphere, remaining as subneptunes. Webb has observed several planets near this dividing line, catching them potentially in the act of transitioning from one category to another. Webb's observations have also revealed the importance of planetary geology in shaping surface conditions. On airless worlds, Webb can directly observe the surface composition by analyzing the spectrum of thermal emission from the dayside. Different minerals emit infrared radiation differently, creating spectroscopic signatures that Webb can detect. Observations of LHS 3844b, for instance, revealed spectral features consistent with a basaltic surface, similar to the dark volcanic plains on the Moon and Mercury. But some rocky planets show evidence of much more exotic geology. The planet 55 Cancri E, a super-Earth orbiting extremely close to its Sun-like star, has a dayside temperature exceeding 2000 Kelvin. At these temperatures, rock doesn't just melt, it vaporizes. Webb's observations suggest this planet might have an atmosphere of vaporized rock, with silicon monoxide and other rock-forming minerals existing as gases. On the night side, these gases might condense and rain down as liquid lava, creating a rock cycle unlike anything in our solar system. The potential for plate tectonics on exoplanets has important implications for habitability. On Earth, plate tectonics plays a crucial role in regulating climate through the carbon cycle, recycling carbon dioxide between the atmosphere and the planet's interior. Webb can't directly observe plate tectonics, but it can look for indirect signs, such as volcanic gases in the atmosphere that might indicate active geology. The planet LP8909c showed intriguing hints of possible geological activity. Webb detected what might be sulfur dioxide in its atmosphere, a gas that on Earth is primarily produced by volcanoes. While other explanations are possible, the potential detection of volcanic gases on an exoplanet opens exciting possibilities for understanding the geological processes that shape these distant worlds. Water, the essential ingredient for life as we know it, has been a primary target of Webb's observations of rocky planets. Detecting water vapor in the atmosphere of a rocky planet in the habitable zone would be a major step toward finding potentially habitable worlds. But water is surprisingly difficult to detect on Earth-sized planets. The spectroscopic features of water are often masked by clouds or confused with other molecules. Additionally, water vapor high in the atmosphere, where it's easier to detect, might not indicate surface water. Webb's observations of K2-18b initially excited the scientific community with the detection of water vapor in what appeared to be a potentially habitable world. However, further analysis revealed that this planet is likely a mini-Neptune with a thick hydrogen atmosphere rather than a rocky world with surface water. This discovery highlighted the importance of comprehensive observations to correctly interpret atmospheric signals. The concept of ocean worlds, planets entirely covered by deep oceans, has gained attention through Webb's observations. These worlds, with no land surface, would have very different climates and chemistry than Earth. Webb's observations of several sub-Neptune planets suggest some might have water-rich compositions, potentially representing ocean worlds with thick steam atmospheres. The planet TOI270d, for instance, shows spectroscopic hints of a water-dominated atmosphere that could indicate an ocean world beneath. The interaction between stellar radiation and planetary surfaces creates diverse and sometimes unexpected environments on rocky exoplanets. Tidally locked planets, which always show the same face to their star, develop extreme temperature gradients between their permanent day and night sides. Webb has observed how these gradients drive powerful winds and affect atmospheric chemistry and cloud formation. The planet WASP-121b, while technically a hot Jupiter, demonstrates principles that apply to smaller tidally locked worlds. Webb observed that the dayside is hot enough to break apart water molecules into hydrogen and oxygen, while the nightside is cool enough for these atoms to recombine into water. This creates a cycle where water is destroyed on the dayside and reformed on the nightside, with powerful winds carrying the constituents between the two hemispheres. For potentially habitable tidally locked planets, this day-night dichotomy creates unique challenges and opportunities for life. The dayside might be too hot and dry for life, while the nightside might be frozen solid. But the terminator region, the twilight zone between day and night, might offer stable, moderate conditions where liquid water could exist and life could potentially thrive. Webb's observations of tidally locked rocky planets are helping scientists understand how heat and moisture are transported on these worlds and where habitable conditions might exist. The role of clouds in shaping the climate of rocky exoplanets has proven more complex than anticipated. Clouds can cool a planet by reflecting starlight, but they can also warm it by trapping infrared radiation. The type of clouds, their altitude, and their coverage all affect their climate impact. Webb's observations have revealed diverse cloud compositions on rocky exoplanets, from water clouds similar to Earth's to exotic clouds of minerals and metals. On the planet GJ3470b, Webb detected what appears to be high-altitude clouds that significantly affect the planet's energy balance. These clouds reflect enough starlight to keep the planet cooler than it would be with a clear atmosphere, potentially expanding the range of distances from the star where the planet could maintain liquid water on its surface. This discovery suggests that clouds might make more planets potentially habitable than previously thought. The detection of impact events on exoplanets represents an exciting new capability enabled by Webb sensitivity. Large impacts can temporarily alter a planet's atmosphere, ejecting material into space and creating temporary atmospheres on otherwise airless worlds. While Webb hasn't yet observed an impact in real time, it has detected what might be impact debris around several young stars where planets are still forming. These observations provide insights into the late stages of planet formation when worlds experience heavy bombardment similar to what Earth experienced early in its history. The gas giants observed by the James Webb Space Telescope have revealed themselves to be far more diverse and complex than we ever imagined. These massive worlds, composed primarily of hydrogen and helium but enriched with heavier elements in ways that continue to surprise us, serve as natural laboratories for understanding physics and chemistry under extreme conditions. From scorching hot Jupiters with atmospheres of vaporized metal to cold giants in the outer reaches of their solar systems, each observation has expanded our understanding of planetary formation, evolution, and the incredible diversity of worlds that exist in our galaxy. The hot Jupiters, those gas giants orbiting extraordinarily close to their stars, have provided some of Webb's most spectacular discoveries. These planets, unknown in our own solar system, exist in a regime where temperatures soar above 2000 Kelvin, where the distinction between day and night creates weather patterns of unimaginable violence, and where chemistry operates in ways that would seem impossible under Earth conditions. WSP-76b exemplifies these extreme worlds. Webb's observations revealed that on the day side of this planet, temperatures exceed 2500 Kelvin, hot enough to vaporize iron. The iron vapor is then carried by winds exceeding 5,000 km per hour to the night side, where it condenses and literally rains liquid iron. The precision of Webb's measurements has allowed scientists to create detailed weather maps of these alien worlds. The planet WSP-18b, one of the most massive hot Jupiters known, shows a fascinating atmospheric structure. Webb detected a strong temperature inversion in its atmosphere, where temperatures increase with altitude rather than decrease. This inversion is caused by molecules high in the atmosphere absorbing starlight and heating up, similar to how ozone creates a temperature inversion in Earth's stratosphere. But on WSP-18b, the absorbing molecules are exotic species like titanium oxide and vanadium oxide, which only exist as gases at extreme temperatures. The chemical diversity Webb has uncovered in gas giant atmospheres challenges our understanding of planetary formation. Classical models suggested that gas giants should have compositions similar to their host stars, perhaps slightly enriched in heavy elements. But Webb's observations have revealed planets with compositions that deviate significantly from these expectations. The planet WSP-127b, for instance, shows an atmosphere surprisingly depleted in water but enriched in carbon monoxide, suggesting it formed in a region of its protoplanetary disk with unusual chemistry or underwent processes that altered its composition after formation. The ability to measure precise chemical abundances has opened a new window into the formation history of gas giants. The ratio of carbon to oxygen in a planet's atmosphere serves as a tracer of where in the protoplanetary disk the planet formed. Water ice, which is rich in oxygen, condenses at different distances from the star than other molecules like carbon dioxide or methane. By measuring these ratios, Webb can determine whether a planet formed beyond the water-ice line and migrated inward, or formed in place near its current orbit. HD 149026b, also known as KLT23b, provided a perfect case study for this technique. Webb's observations revealed a carbon-to-oxygen ratio significantly higher than the host stars, indicating the planet likely formed far from its current position. Beyond multiple ice lines where it could accumulate carbon-rich ices. The planet must have then migrated inward through gravitational interactions with the disk or other planets, ending up in its current 3-day orbit around the star. The phenomenon of atmospheric escape has been observed in exquisite detail by Webb. Many hot Jupiters are losing their atmospheres to space at prodigious rates, creating comet-like tails of gas streaming away from the planet. HAT P32b is losing mass so rapidly that it will be completely stripped of its atmosphere in a few billion years. Webb has detected the escaping hydrogen and helium, but more remarkably, it has also detected heavier elements like magnesium and iron being carried away by the escaping gas. This process, called hydrodynamic escape, occurs when the upper atmosphere becomes so hot that gas particles achieve escape velocity. The study of cooler gas giants, those more similar to Jupiter and Saturn in our own solar system, has revealed unexpected complexity in their atmospheric chemistry and structure. These planets, receiving less stellar radiation than hot Jupiters, have chemistry dominated by methane, ammonia, and water, molecules familiar from our solar system giants. But Webb's precision has revealed subtle variations that tell us about processes deep within these planets. WSP-80b, a warm Jupiter with a temperature around 800 Kelvin, showed an unexpected abundance pattern in its atmosphere. Webb detected not just the expected methane, but also evidence of phosphine, a molecule that in Jupiter's atmosphere is dredged up from the deep interior by convection. The presence of phosphine in WSP-80b suggests similar deep convective processes, providing a window into the planet's internal structure and dynamics that would be impossible to observe directly. The discovery of clouds and hazes with exotic compositions has been one of Webb's most visually striking findings. In addition to the iron clouds in ultra-hot Jupiters, Webb has detected clouds made of silicates, essentially sand, aluminum oxide, sapphire and ruby, and even more exotic materials. The planet WSP-96b shows evidence of multiple cloud layers at different altitudes, each with different compositions depending on the temperature at that level. The result is a complex, layered atmosphere where different minerals condense and evaporate as gases move up and down. The role of photochemistry in gas giant atmospheres has been illuminated by Webb's observations. Ultraviolet light from the star can break apart molecules in the upper atmosphere, creating a complex web of chemical reactions. On WSP-39b, Webb detected sulfur dioxide, a product of photochemistry similar to the process that creates ozone in Earth's atmosphere. But the photochemistry in hot Jupiter atmospheres operates at much higher temperatures and with different starting molecules, creating products we never see in our solar system. The dynamics of atmospheric circulation on gas giants have been revealed in unprecedented detail. Webb has observed how heat is transported from the permanently sunlit day side to the dark night side on tidally locked planets. The efficiency of this heat transport varies dramatically between planets, depending on factors like atmospheric composition, planetary rotation rate, and the strength of atmospheric winds. Some planets show very efficient heat redistribution, with relatively small day-night temperature differences, while others show extreme contrasts with temperature differences exceeding 1000 Kelvin. WSP-43b provided a particularly detailed look at atmospheric dynamics. Webb created a phase curve of this planet, observing how its brightness changes as different parts of the planet rotate into view. The observations revealed that the hottest point on the planet isn't directly beneath the star, but shifted eastward by strong equatorial winds. These winds, moving at speeds of thousands of kilometers per hour, carry heat eastward faster than the planet rotates, creating this offset hot spot. The interaction between gas giant atmospheres and their magnetospheres has been indirectly observed through Webb. While the telescope can't detect magnetic fields directly, it can see their effects. On several gas giants, Webb has detected emission from ionized gases high in the atmosphere, possibly auroral emission similar to the northern lights on Earth but far more powerful. These observations suggest that many gas giants have strong magnetic fields that interact with the stellar wind, creating spectacular auroral displays that would dwarf anything seen in our solar system. The discovery of chemical gradients in gas giant atmospheres has revealed the three-dimensional structure of these worlds. Webb can observe how chemical abundances vary with altitude, latitude, and longitude. On the ultra-hot Jupiter KLT9b, the day side is so hot that even molecules like hydrogen are partially dissociated into individual atoms. But on the night side, these atoms recombine into molecules. Webb has observed this dissociation and recombination in action, tracking how molecular hydrogen breaks apart on the day side and reforms on the night side. The presence of heavy elements in gas giant atmospheres tells stories about planetary formation and evolution. Webb has detected a wide range of metals in gas giant atmospheres, from alkali metals like sodium and potassium to transition metals like iron and titanium. The abundance of these elements relative to hydrogen provides clues about how much solid material the planet accumulated during its formation. Planets with higher metal content likely formed in regions of the protoplanetary disk enriched in solid materials or accumulated more planetesimals during their growth. Webb's observations of young gas giants still in the process of forming have provided direct insights into planetary birth. The planet PDS-70b, only a few million years old, is still glowing from the heat of its formation. Webb's infrared observations can peer through the dusty disk surrounding the young star to observe the planet directly. The spectrum of this young world shows evidence of active accretion, with gas still falling onto the planet and releasing energy. These observations provide a direct look at how gas giants grow and evolve in their earliest stages. The phenomenon of radius inflation in hot Jupiters has been a long-standing puzzle that Webb is helping to solve. Many hot Jupiters have radii larger than models predict, as if they're puffed up by some additional heat source. Webb's precise measurements of atmospheric composition and temperature structure are providing clues to this mystery. Some planets show evidence of increased atmospheric opacity from clouds or hazes, which could trap heat and inflate the planet. Others show signs of atmospheric dynamics that might transport energy deep into the planet's interior. The discovery of companion planets to known gas giants has been enabled by Webb's exceptional sensitivity and resolution. In several systems, Webb has detected additional planets that were too faint to see with previous telescopes. These discoveries are reshaping our understanding of planetary system architectures. The HR 8799 system, for instance, was thought to have one giant planet, but Webb revealed it actually has multiple planets, each carving gaps in the system's debris disk. The chemical diversity of gas giants extends to isotope ratios, which Webb can measure with unprecedented precision. The ratio of carbon-12 to carbon-13, or oxygen-16 to oxygen-18, provides information about the temperature and location where these elements were incorporated into the planet. These isotopic fingerprints can reveal whether a planet formed from material that was processed at high temperatures near the star or from pristine material in the cold outer disk. Among the thousands of exoplanets studied by the James Webb Space Telescope, some stand out as truly extraordinary, defying our expectations and forcing us to reconsider what we thought we knew about planetary science. These worlds, with their bizarre properties and extreme conditions, have expanded our conception of what a planet can be and challenged our theories of planetary formation and evolution. Each of these discoveries tells a unique story about the creative power of the universe in crafting worlds beyond our wildest imagination. The planet GJ504b represents one of the most puzzling discoveries Webb has made. This world, only slightly larger than Earth, orbits its star in just 33 hours, making it one of the shortest period rocky planets known. But what makes it truly extraordinary is its surface composition. Webb spectroscopic observations suggest the planet's surface might be covered in graphite, essentially a world wrapped in pencil lead. This bizarre composition likely results from the planet being the exposed core of what was once a much larger world, stripped of its outer layers by billions of years of stellar radiation. The carbon-rich core, now exposed to space, has been transformed by the intense heat into a graphite crust unlike anything in our solar system. The discovery of rogue planets, worlds wandering through interstellar space without a parent star, has been one of Webb's most haunting achievements. These lonely worlds, ejected from their birth systems by gravitational interactions, drift through the darkness between stars. Webb detected several of these rogue planets through their faint infrared glow, the residual heat from their formation still radiating into the cosmic void. One particularly intriguing rogue planet, designated WYS-0855, is only a few light-years from Earth and has a temperature below the freezing point of water. Yet Webb's observations suggest it might have clouds in its atmosphere, possibly made of water ice crystals, creating weather patterns on a world that has never seen a sunrise. The binary planet system ROX's 42BB has challenged our understanding of what constitutes a planet versus a brown dwarf. This object, about 9 times the mass of Jupiter, orbits a binary star system at an enormous distance, about 150 times the Earth-Sun distance. But Webb's observations revealed that this planet actually has a companion of its own, another massive object orbiting around it. This creates a hierarchical system where planets orbit around planets that orbit around stars, a configuration that blurs the line between planetary systems and multiple star systems. Perhaps no discovery has been more spectacular than the detection of clouds made of quartz crystals in the atmosphere of WASP-17b. This planet, notable for being one of the puffiest gas giants known with a density less than Cork, has an atmosphere where conditions are just right for silicon dioxide to condense into tiny crystals of pure quartz. These crystals, each smaller than a grain of sand, create clouds that sparkle with reflected starlight. Webb's observations showed that these clouds create a shimmering haze that extends far above the planet's visible atmosphere, creating what would be an incredibly beautiful if utterly alien sky. The planet TOI 5205b has revealed itself to be a world of permanent twilight. This unusual planet orbits in perfect resonance with another planet in its system, locked in a gravitational dance that keeps one hemisphere in eternal dawn and the other in eternal dusk. Webb's observations showed that this unique lighting condition has created a climate unlike any other observed. The planet has a ribbon of clouds that circles the terminator line, where temperatures are just right for condensation, while the rest of the planet remains clear. This creates a world with a permanent sunset wrapped around its middle, a poetic configuration that demonstrates the universe's capacity for creating beauty in unexpected ways. The ultra-hot Jupiter KLT9b stands as one of the most extreme planets ever discovered, with a dayside temperature exceeding 4,300 Kelvin, hotter than many stars. Webb's observations of this infernal world revealed that its atmosphere is so hot that molecules are torn apart into their constituent atoms. Even hydrogen molecules, the most stable molecules in the universe, dissociate on the dayside. But what makes this planet truly extraordinary is what Webb discovered about its atmospheric composition. The telescope detected rare Earth elements like yttrium and scandium in gaseous form, elements that on Earth only exist as gases in the most extreme industrial processes. This planet's atmosphere is essentially a natural particle accelerator, creating conditions that physicists struggle to reproduce in laboratories. The discovery of a planet orbiting a white dwarf star, WD 1856+124, represents one of Webb's most profound achievements. White dwarfs are the remnants of dead stars, the cooling embers left after a star like our Sun exhausts its nuclear fuel. Any planets that orbited close to such a star would have been destroyed when it expanded into a red giant before collapsing into a white dwarf. Yet Webb discovered a giant planet orbiting this stellar corpse, likely a world that migrated inward after the star's death or formed from the debris disk left behind. This discovery proves that planetary systems can survive, or even form anew, after their star's death, suggesting that the universe's capacity for creating worlds extends even beyond stellar lifetimes. The planet HD 106906b has earned the nickname, the planet that shouldn't exist. This world orbits its star at a distance where tidal forces should have long ago torn it apart or caused it to spiral into the star. Yet it persists, defying our understanding of orbital dynamics. Webb's observations revealed that the planet has an unusually strong internal heat source, glowing far brighter in the infrared than its age would suggest. Some scientists theorize that the planet might be sustained by a previously unknown energy source, perhaps tidal heating from an unseen companion or radioactive decay of unusual isotopes in its core. This world reminds us that our models of planetary physics are still incomplete. The discovery of a planet with retrograde rotation, WSP-2b, has puzzled astronomers since Webb revealed its atmospheric dynamics. While the planet orbits its star in the normal direction, its atmosphere rotates backward, with winds blowing opposite to the planet's rotation. This creates a unique situation where the planet's surface, if it has one beneath its thick atmosphere, experiences winds always blowing from east to west at thousands of kilometers per hour. Webb's observations suggest this might be caused by atmospheric tides raised by the star's gravity, but the exact mechanism remains mysterious. This backward world demonstrates that even basic planetary properties we take for granted can be reversed in alien environments. The planet K2141b has revealed itself to be a world of diamond rain. This Neptune-sized planet has an atmosphere rich in carbon, and Webb's observations indicate that deep in the atmosphere, where pressures exceed millions of times Earth's surface pressure, methane breaks down and carbon atoms are squeezed into diamond crystals. These diamonds then rain down through the atmosphere like hail, possibly accumulating in a layer of diamond hundreds of kilometers thick. While diamond rain has been theorized to occur on Neptune and Uranus in our own solar system, K2141b is the first exoplanet where we have observational evidence for this extraordinary phenomenon. Webb's discovery of planets in the habitable zones of binary star systems has opened new possibilities for life in the universe. The planet Kepler-16b, nicknamed Tatooine after the fictional Star Wars world, orbits two stars that orbit each other. Webb's observations revealed that despite the complex gravitational environment and variable stellar radiation, the planet maintains a surprisingly stable climate. The two stars create a complex pattern of seasons, with the planet experiencing double sunrises and sunsets, and periods where one star eclipses the other. This stability suggests that planets in binary systems, which make up a large fraction of all star systems, might be more habitable than previously thought. The ultra-dense planet TOI849b has a density greater than iron, making it one of the densest planets known. This world, about 90% the size of Earth, has a mass nearly twice Earth's, giving it a surface gravity that would crush any human visitor. Webb's observations suggest this planet might be the exposed core of a former gas giant, stripped of its atmosphere and outer layers by stellar radiation. But the planet's spectrum shows traces of a thin secondary atmosphere, possibly volcanic gases emerging from the planet's interior. This suggests the planet is still geologically active, with an interior so compressed that exotic forms of matter might exist in its core. The discovery of a planet with a figure-8 orbit, HD 80606b, represents one of the most unusual orbital configurations ever observed. This planet's orbit is highly eccentric and inclined, causing it to trace a figure-8 pattern relative to the stars in its binary system. Webb's observations over multiple orbits revealed that this creates extreme seasonal variations, with the planet sometimes receiving radiation from both stars simultaneously and sometimes passing through the shadow of one star while being illuminated by the other. The planet's atmosphere responds to these variations in complex ways, with chemical compositions and cloud patterns changing dramatically over its orbital period. The planet GJ3053b exists in a state of permanent hurricane. This world, tidally locked to its star, has developed a global storm system where the entire atmosphere circulates in a single, planet-wide vortex. Webb's observations showed wind speeds exceeding 8,000 km per hour at the equator, fast enough to circle the planet in less than 10 hours. The storm is driven by the extreme temperature difference between the day and night sides, creating a convection pattern unlike anything seen before. At the center of the day side, where the star's heat is most intense, gases rise so violently that they escape into space, creating a fountain of atmospheric loss that the planet replenishes from volcanic outgassing. The discovery of a planet that pulses like a heartbeat, HAT-P2b, has revealed a new type of planetary behavior. This gas giant experiences enormous tidal forces from its star that cause the entire planet to stretch and compress over its orbital period. Webb detected these pulsations through variations in the planet's infrared brightness, as the compression heats the interior and causes it to glow more brightly. The pulsations are so regular that they could be used as a cosmic clock, keeping time with extraordinary precision. This tidal heating might explain why some hot Jupiters remain inflated despite theoretical predictions that they should contract as they cool. The planet HD 2030b has been revealed by Webb to have the most eccentric orbit of any known exoplanet, swinging from scorching proximity to its star out to the frigid depths of its solar system. At its closest approach, the planet comes within a few stellar radii of its star's surface, experiencing temperatures above 3000 Kelvin. At its farthest point, it retreats to distances where water would freeze instantly. Webb tracked this planet through a complete orbit, observing how its atmosphere responds to these extreme variations. During close approach, the atmosphere puffs up and material streams away from the planet. As it retreats to cold distances, the atmosphere collapses and freezes out, creating a cycle of atmospheric death and rebirth with each orbit. The discovery of a planet with metallic hydrogen rain, WSP-76b, pushes the boundaries of extreme weather. On this ultra-hot Jupiter, conditions are so extreme that hydrogen, normally a gas, behaves like a liquid metal. Webb detected signatures suggesting that metallic hydrogen forms in the planet's interior and is carried upward by convection. When it reaches lower pressure regions, it transforms back into molecular hydrogen in a process that releases enormous amounts of energy, driving violent storms. The metallic hydrogen rain would appear as glowing droplets of liquid metal falling through the atmosphere, a sight that would be both beautiful and terrifying. Webb has discovered several planets that challenge our understanding of atmospheric chemistry by having atmospheres that glow in unusual colors. The planet HAT-P70b, for instance, glows a deep purple in certain infrared wavelengths due to the presence of vanadium oxide in its atmosphere. This molecule absorbs green and blue light but transmits red and violet, creating the purple glow. Another planet, WASP-103b, glows green due to the presence of unusual chromium compounds. These colored worlds demonstrate the chemical diversity possible in exoplanet atmospheres and remind us that alien skies might come in colors we've never imagined. The discovery of a planet with glass rain, HD 189733b, reveals weather of extraordinary violence. This blue-colored world has an atmosphere containing silicate particles that condense into glass droplets. But unlike gentle rain on Earth, these glass droplets are carried sideways by winds exceeding 7,000 km per hour, creating a horizontal rain of molten glass that would shred anything in its path. Webb's observations showed that the glass particles create a deep blue color by preferentially scattering blue light, similar to why Earth's sky is blue but through a completely different mechanism. The extraordinary discoveries made by the James Webb Space Telescope aren't just the result of its powerful hardware but also the ingenious observational techniques and data analysis methods developed by astronomers to extract every bit of information from the light gathered by this remarkable instrument. Understanding how Webb actually observes exoplanets, how scientists process and interpret the data, and how they overcome the enormous challenges involved reveals the true sophistication of modern exoplanet science. The transit method remains one of Webb's primary tools for studying exoplanets, but the telescope has elevated this technique to an art form. When a planet passes in front of its star from our perspective, it blocks a tiny fraction of the star's light. For an Earth-sized planet orbiting a Sun-like star, this dimming is only about 84 parts per million, equivalent to detecting the dimming caused by a gnat flying in front of a lighthouse from several kilometers away. Webb achieves this precision through a combination of its large mirror, which gathers enough photons to reduce statistical noise, and its incredibly stable pointing, which ensures the measurements aren't contaminated by the telescope's own motion. But Webb doesn't just measure the total dimming during a transit. It performs transmission spectroscopy, spreading the star's light into its component wavelengths and measuring how the transit depth changes with wavelength. When starlight passes through the planet's atmosphere during a transit, different molecules absorb different wavelengths of light. By measuring these wavelength-dependent variations in transit depth, Webb can identify what molecules are present in the atmosphere. The challenge is that these variations are even tinier than the transit itself, often just a few parts per million, requiring multiple transits to build up enough signal to make confident detections. The preparation for a transit observation begins long before the planet actually passes in front of its star. Scientists must precisely predict when the transit will occur, accounting for light travel time from the star to Earth and any changes in the planet's orbital period. Webb schedulers then need to ensure the telescope is available and properly oriented at exactly the right time. For planets with orbital periods of many days or weeks, this requires careful planning months or even years in advance. During the observation itself, Webb stares continuously at the star for hours, taking measurements every few seconds. The telescope observes the star before the transit begins to establish a baseline, then watches as the planet slowly moves in front of the star, and continues observing after the transit ends. This continuous observation is crucial for removing systematic effects and ensuring the detected signal is real. The data volume is enormous, with a single transit observation potentially generating gigabytes of data that must be transmitted back to Earth and processed. The secondary eclipse technique, where Webb observes as the planet passes behind its star, provides complementary information to transits. Just before the planet disappears behind the star, Webb measures the combined light from both the star and the planet's dayside. When the planet is hidden, only the star's light remains. The difference tells us how much light is coming from the planet itself. For hot planets, this is primarily thermal emission, allowing Webb to measure the planet's temperature. For cooler planets, it might include reflected starlight, providing information about clouds and surface properties. Phase curve observations take this concept further by observing the planet continuously as it orbits its star. As different parts of the planet rotate into view, the total brightness changes, creating a phase curve similar to the phases of the Moon but measured in infrared light. These observations reveal how heat is distributed across the planet, from the hot day side to the cool night side. They can detect hot spots, cold traps, and the efficiency of atmospheric circulation. Phase curves require observing for at least one complete orbital period, which for close-in planets might be a few days of continuous observation. Direct imaging, actually taking pictures of exoplanets, pushes Webb to its absolute limits. The challenge is separating the faint light of a planet from the overwhelming glare of its star. Webb uses coronagraphs, devices that block the star's light, similar to using your hand to block the sun when looking for something near it in the sky. But even with a coronagraph, the star's light diffracts around the blocking disk, creating patterns that can hide or mimic planetary signals. Sophisticated image processing techniques, including angular differential imaging where the telescope rotates to distinguish real planets from artifacts, are essential for successful direct imaging. The data processing pipeline for Webb's exoplanet observations is a marvel of computational sophistication. Raw data from the telescope contains not just the signal from the target but also noise from various sources, cosmic rays hitting the detector, thermal fluctuations in the instruments, and systematic patterns from the detector itself. The first step is calibrating the data, removing known instrumental effects using calibration files created from dedicated observations of standard stars and internal calibration sources. Next comes the extraction of the stellar spectrum from the two-dimensional detector images. This involves tracing the spectrum across the detector, accounting for optical distortions, and carefully summing the light while avoiding contamination from nearby stars or bad pixels. The precision required is extraordinary, as errors at this stage can introduce systematic effects that mimic or hide planetary signals. The removal of stellar variability presents another challenge. Stars aren't perfectly stable, they have spots, flares, and oscillations that can change their brightness. These variations can be much larger than the planetary signals we're trying to detect. Scientists use various techniques to remove these effects, including observing in wavelength ranges where stellar variability is minimized, using the star's rotation period to model spot patterns, and simultaneously fitting for stellar and planetary signals. One of the most powerful techniques Webb employs is differential spectroscopy, comparing observations at different wavelengths to remove systematic effects that affect all wavelengths equally. For instance, if the telescope's pointing drifts slightly during an observation, it will affect all wavelengths the same way. By looking at the difference between wavelengths where a molecule absorbs and where it doesn't, scientists can isolate the molecular signature from systematic effects. The analysis of Webb's data often involves sophisticated atmospheric models that simulate how light passes through or is emitted by exoplanet atmospheres. These models account for the temperature and pressure structure of the atmosphere, the abundance of different molecules, the presence of clouds and hazes, and the scattering and absorption of light at different wavelengths. By comparing observed spectra with millions of model spectra, scientists can determine which atmospheric properties best explain the observations. Machine learning and artificial intelligence have become increasingly important in analyzing Webb's exoplanet data. Neural networks can be trained to recognize planetary signals in noisy data, to remove systematic effects, and to extract atmospheric properties from spectra. These techniques are particularly valuable for finding weak signals that might be missed by traditional analysis methods and for handling the enormous data volumes that Webb produces. The cross-correlation technique has proven particularly powerful for detecting specific molecules in exoplanet atmospheres. This method involves comparing the observed spectrum with a template spectrum of the molecule of interest, shifted to different velocities. When the template matches the planet's velocity, the correlation strengthens, revealing the molecule's presence even when individual spectral lines are too weak to detect. This technique has allowed Webb to detect molecules that would be invisible to traditional methods. Webb's ability to observe in multiple modes simultaneously or in rapid succession has opened new possibilities for exoplanet characterization. For instance, the telescope can take images while also obtaining spectra, allowing scientists to study both the spatial distribution and composition of features like atmospheric storms or volcanic plumes. The ability to quickly switch between different filters or spectroscopic modes enables observations of transient phenomena that would be missed by slower telescopes. The time series stability of Webb's instruments has been crucial for exoplanet observations. Many systematic effects that plague ground-based telescopes, such as atmospheric turbulence and changing weather, are absent in space. Webb's detectors have proven remarkably stable over hours-long observations, with noise levels close to the theoretical limits set by photon statistics. This stability allows for the detection of signals that would be impossible to see from the ground. As we look toward the remaining years of the James Webb Space Telescope's mission, the future of exoplanet science appears brighter than ever. The telescope, having exceeded all performance expectations, continues to revolutionize our understanding of worlds beyond our solar system. The observations planned for the coming years promise to push the boundaries of what we can learn about exoplanets, from potentially habitable worlds that might harbor life to bizarre planets that challenge our understanding of planetary physics. The search for biosignatures in the atmospheres of potentially habitable planets represents perhaps the most ambitious goal for Webb's future observations. While the telescope wasn't specifically designed to detect life, its capabilities make it possible to search for certain chemical signatures that might indicate biological activity. The simultaneous presence of oxygen and methane, for instance, would be difficult to explain without life, as these gases react with each other and shouldn't coexist in equilibrium. Webb's continued observations of planets in the habitable zones of nearby stars are slowly building up the signal-to-noise ratio needed to detect such biosignatures if they exist. The TRAPPIST-1 system remains a primary target for these searches. With 7 Earth-sized planets, 3 of which orbit in the habitable zone, this system offers multiple chances to find a potentially habitable world. Each transit of these planets adds a small amount of information to our understanding of their atmospheres. Scientists estimate that with enough observations over Webb's lifetime, we should be able to definitively determine whether the potentially habitable TRAPPIST-1 planets have atmospheres and what those atmospheres are made of. The discovery of water vapor, oxygen, or other biosignature gases in one of these worlds would be one of the most profound discoveries in human history. Beyond the TRAPPIST-1 system, Webb has identified several other promising targets for biosignature searches. LHS 1140b and C, 2 Earth-sized planets orbiting a nearby red dwarf, are receiving intensive study. The planet LP 890-9c, which shows hints of possible volcanic activity, is being monitored for changes that might indicate active geology, a potential requirement for habitability. Each of these worlds offers a unique opportunity to understand the conditions necessary for life and the signatures it might produce. The study of planetary system architectures is revealing patterns that help us understand how planetary systems form and evolve. Webb's ability to detect smaller, more distant planets in known systems is showing that many systems have complex architectures with multiple planets in resonant chains, where the orbital periods form simple integer ratios. These resonances tell stories about planetary migration, as planets must move slowly and gently to maintain these delicate orbital relationships. Understanding these architectures helps us place our own solar system in context and understand whether systems like ours are common or rare. The investigation of planet formation is being revolutionized by Webb's ability to peer through the dusty disks around young stars. The telescope is observing protoplanetary disks at different stages of evolution, from young disks just beginning to form planets to older debris disks where planet formation is complete. These observations are revealing how planets form in real time, showing gaps and rings carved by forming planets, spiral arms driven by gravitational interactions, and the chemical evolution of disk material as it's processed into planets. In the PDS-70 system, Webb is monitoring young planets that are still actively accreting material. By observing how these planets grow over time, scientists can test theories of planet formation that until now have been based primarily on computer simulations. The discovery of planets forming in unexpected locations, such as very far from their stars or in binary systems, is forcing a reconsideration of planet formation theories. The characterization of super-Earths and mini-Neptunes, the most common types of planets in the galaxy but absent from our solar system, continues to be a major focus. These planets occupy a size range between Earth and Neptune where the transition from rocky to gaseous occurs. Webb is slowly mapping out this transition, determining which factors control whether a planet becomes a large rocky world or a small gas planet. Understanding these worlds is crucial for determining the frequency of potentially habitable planets, as some super-Earths might be scaled-up versions of Earth while others might be scaled-down versions of Neptune. The exploration of extreme environments on exoplanets is revealing the limits of planetary physics. Ultra-hot Jupiters with temperatures exceeding 4,000 Kelvin are being used as laboratories to study chemistry and physics under conditions impossible to recreate on Earth. The discovery of exotic phenomena like metallic hydrogen rain, diamond precipitation, and rock vapor atmospheres is expanding our understanding of material properties under extreme conditions. These observations have applications beyond astronomy, informing high-pressure physics and chemistry research. The study of atmospheric dynamics and weather on exoplanets is becoming increasingly sophisticated. Webb is creating detailed weather maps of exoplanets, tracking storm systems, measuring wind speeds, and observing how weather patterns change over time. The goal is to develop a general theory of atmospheric dynamics that can explain weather on worlds ranging from Earth-like planets to hot Jupiters. This understanding is crucial for interpreting biosignatures, as we need to understand how atmospheric dynamics might concentrate or dilute biological gases. The investigation of habitability is expanding beyond the traditional habitable zone concept. Webb is studying planets that might be habitable through mechanisms other than stellar heating. Moons of giant planets might be heated by tidal forces, maintaining liquid oceans beneath ice shells. Rogue planets might retain heat from radioactive decay or residual formation energy. Planets with thick hydrogen atmospheres might maintain liquid water at distances where they would otherwise be frozen. Each of these scenarios expands the potential real estate for life in the universe. The coordination between Webb and other telescopes, both in space and on the ground, is amplifying the scientific return. Ground-based telescopes are conducting surveys to find new planets for Webb to study in detail. The Hubble Space Telescope continues to work in tandem with Webb, observing at ultraviolet and visible wavelengths that complement Webb's infrared vision. Future telescopes like the Nancy Grace Roman Space Telescope and the European Space Agency's Plato mission will find thousands of new planets for Webb to characterize. The development of new analysis techniques is extracting more information from Webb's data than was thought possible. Advanced statistical methods are finding weak signals buried in noise. Machine learning algorithms are identifying patterns humans might miss. Improved atmospheric models are providing more accurate interpretations of spectra. Each advancement in analysis techniques effectively increases Webb's sensitivity, allowing for the detection of smaller signals and more subtle effects. The legacy of Webb's exoplanet observations will extend far beyond the telescope's operational lifetime. The data being collected now will be analyzed for decades to come, with new discoveries likely as analysis techniques improve. The catalog of characterized exoplanets Webb is creating will serve as the foundation for future missions, identifying the most promising targets for detailed study by next-generation telescopes. The technological developments driven by Webb's requirements are enabling future missions. The techniques developed for Webb's segmented mirror are being applied to even larger telescopes. The stability requirements for exoplanet observations are driving improvements in spacecraft design. The data analysis pipelines created for Webb are being adapted for future missions. In this way, Webb is not just making discoveries but enabling future discoveries. The search for Earth twins, planets truly similar to our own in size, composition, and stellar environment, remains a long-term goal. While Webb can study Earth-sized planets around red dwarf stars, detecting Earth twins around Sun-like stars remains extremely challenging. These planets have smaller signals, longer orbital periods, and orbit brighter stars, making them much harder to study. But Webb is pushing the boundaries, attempting observations that test the absolute limits of its capabilities. The possibility of detecting industrial pollutants or other technosignatures in exoplanet atmospheres has been seriously considered. While extremely challenging, Webb could potentially detect certain artificial compounds like chlorofluorocarbons if they were present in high enough concentrations. The search for technosignatures is a long shot, but the potential payoff, the discovery of technological civilization, makes it worth attempting. The study of exomoons, moons orbiting exoplanets, represents a frontier that Webb is just beginning to explore. While no exomoons have been definitively detected yet, Webb has the sensitivity to detect large moons around giant planets. These moons might be more habitable than the planets they orbit, especially around giant planets in the habitable zone. The discovery and characterization of exomoons would add another dimension to our understanding of planetary systems. As we draw near the end of our cosmic journey through the revolutionary discoveries of the James Webb Space Telescope, we find ourselves standing at a profound moment in human history. We are the first generation of humans who can not only dream about worlds beyond our solar system but actually study them in extraordinary detail. The stories of these distant worlds, written in the faint whispers of starlight that has traveled for years or decades or centuries to reach us, remind us of our place in a universe far grander and more diverse than we ever imagined. The James Webb Space Telescope has transformed exoplanets from statistical abstractions into real worlds with their own weather, chemistry, and perhaps even biology. Each spectrum captured, each transit observed, each atmosphere analyzed adds another piece to the vast cosmic puzzle of planetary existence. We've learned that planets are not rare accidents but common outcomes of star formation, that they come in varieties we never imagined, and that the universe is endlessly creative in crafting worlds that challenge our understanding and expand our horizons. Think about what we've discovered in just these first years of Webb's mission. We've seen worlds where it rains iron and glass, where diamonds fall like snow, where rocks vaporize into atmospheric mist. We've detected the chemical signatures of water, methane, carbon dioxide, and dozens of other molecules in the atmospheres of planets light years away. We've witnessed the birth of planets in dusty disks around young stars and observed the final orbits of worlds around stellar corpses. We've pushed closer than ever to answering that ancient question that has haunted humanity since we first looked up at the stars: are we alone? The precision and sensitivity of Webb's observations have revealed that even seemingly simple measurements hide layers of complexity. A transit isn't just a dimming of light but a treasure trove of information about atmospheric composition, temperature structure, and cloud properties. A spectrum isn't just a rainbow of colors but a detailed chemical fingerprint that tells stories of formation, evolution, and ongoing processes. Every photon captured by Webb's golden mirror carries information across the vast emptiness of space, connecting us to worlds we may never visit but can now begin to understand. The diversity of exoplanets discovered by Webb has profound implications for our understanding of our own solar system. Earth, with its liquid water oceans, oxygen-rich atmosphere, and abundant life, no longer seems like an inevitable outcome of planetary formation but rather one possible outcome among countless alternatives. Our gas giants, Jupiter and Saturn, Uranus and Neptune, are not templates that all planetary systems follow but merely examples from a vast spectrum of possibilities. This perspective is both humbling and exciting, reminding us that we still have much to learn about how planets form and evolve. The search for life beyond Earth has been transformed from science fiction to serious science. While we haven't yet found definitive evidence of life on another world, Webb has shown us that the tools and techniques needed for such a discovery are within our grasp. We can detect water vapor in the atmospheres of potentially habitable worlds. We can search for the chemical disequilibrium that might indicate biological processes. We can study the conditions on alien worlds to understand whether they might support life as we know it or perhaps life as we don't know it. The implications of these discoveries extend beyond astronomy and into philosophy, theology, and our understanding of our place in the universe. If planets are common, and if many of them have conditions suitable for life, then it seems almost inevitable that life exists elsewhere. The discovery of even simple microbial life on another world would be one of the most significant discoveries in human history, fundamentally changing our perspective on our place in the cosmos. And if we were to discover evidence of complex life or even intelligence, it would mark a turning point in the story of humanity. But even without the discovery of life, the study of exoplanets enriches our understanding of what it means to be human on this pale blue that we call home. Every sunset you witness is made more precious by the knowledge that on WASP 76b, the sunset would be accompanied by iron rain. Every gentle breeze is made more remarkable when compared to the supersonic winds of HD 189733b. Every drop of water is made more valuable knowing how rare liquid water might be in the universe. Webb's discoveries don't diminish Earth's significance but rather highlight how special and precious our world truly is. The technical achievement that Webb represents is itself a testament to human ingenuity and cooperation. Thousands of scientists, engineers, and technicians from dozens of countries worked for decades to make this telescope a reality. They overcame seemingly insurmountable technical challenges, from creating a mirror that could unfold in space to developing detectors sensitive enough to detect the heat from a candle on the moon. The success of Webb demonstrates what humanity can accomplish when we work together toward a common goal of understanding our universe. The data flowing from Webb is available to scientists around the world, embodying the principle that knowledge about the universe belongs to all humanity. A student in India can analyze the same observations as a professor in Canada. An amateur astronomer in Brazil can access the same data as a researcher at NASA. This democratization of cosmic discovery ensures that the benefits of Webb's observations extend to all of humanity, inspiring the next generation of scientists and dreamers. As you drift off to sleep tonight, perhaps you'll dream of these distant worlds that Webb has revealed to us. Maybe you'll imagine standing on the terminator of a tidally locked planet, watching eternal sunset paint the sky in colors that don't exist on Earth. Perhaps you'll envision floating through the clouds of a gas giant where the rain is made of liquid glass and the lightning is 1,000 times more powerful than any storm on Earth. Or maybe you'll dream of a world not so different from our own, with blue skies and white clouds, with oceans and continents, with the possibility of life looking up at their own night sky and wondering if they're alone. The journey of discovery that Webb has begun is far from over. The telescope continues to observe, continues to gather light from distant worlds, continues to push the boundaries of what we can know about planets beyond our solar system. Each observation adds another thread to the tapestry of knowledge we're weaving about our universe. Future telescopes will build on Webb's discoveries, probing even deeper and seeing even clearer. The children watching Webb's discoveries today will be the scientists making discoveries with telescopes we can barely imagine. In the grand story of the universe, we live in a special chapter, the moment when humanity first reached out across the cosmic void to study other worlds in detail. The James Webb Space Telescope is our tool for reading the stories written in starlight, for understanding the incredible diversity of planets that populate our galaxy, and for searching for signs that we are not alone. These stories of distant worlds remind us that we are part of something far greater than ourselves, citizens of a cosmos filled with wonders beyond imagination. As our journey through Webb's exoplanet discoveries comes to a close, remember that this is not an ending but a beginning. Every night, while you sleep, the telescope continues its vigilant watch, gathering ancient light from distant worlds. Tomorrow will bring new discoveries, new mysteries, and new reasons to marvel at the universe we inhabit. The worlds that Webb has revealed to us are not just points of light in the sky but real places with their own stories, their own possibilities, and perhaps their own observers wondering about worlds like ours. Thank you for joining me on this gentle voyage through the cosmos, exploring the remarkable discoveries of the James Webb Space Telescope. As you close your eyes and drift into sleep, carry with you the wonder of these distant worlds, the excitement of discovery, and the profound realization that we live in an age where the impossible has become possible, where we can know the unknowable, and where the universe reveals its secrets to those patient enough to listen to the whispers of starlight. May your dreams be filled with the wonders of distant worlds, and may you wake tomorrow with a renewed sense of awe at the incredible universe we are privileged to explore. If you've enjoyed this cosmic journey, please consider subscribing to hear more stories of the universe's wonders, and remember to like this video to help others discover the remarkable achievements of the James Webb Space Telescope. Until we meet again among the stars, sleep well, dream deeply, and never lose your sense of wonder at the cosmos that surrounds us all. Sweet dreams, fellow travelers, as we drift together through this vast and wondrous universe, connected by our shared curiosity and our eternal quest to understand the worlds beyond our own. The stars are calling, the planets are waiting, and the journey of discovery continues with each new day and each new observation from humanity's great eye in the sky, the James Webb Space Telescope, our window to worlds beyond imagination.